Testing, testing. Yeah, it's working.
Good morning, everybody. Welcome to the first session on distribution and networking. We have 5 super interesting papers, of course, and Feng-Jung Liu will open the session with work on initializing global objects. Floor is yours.
Hello, everyone. Glad to meet you here at UPSNA. I'm Feng Liu from Oracle Labs. I'm going to talk about our work on initializing global objects. This is a joint work with Andrew Notak, David Hua, David is here, and Anderson from University of Waterloo. Programming languages have made great progress on many aspects over the years. However, there is one aspect that hasn't changed much since the beginning of computer programming, that is global variables. Global variables exist in almost all languages, from Fortran to the Latin, Rust, and WebAssembly. Global variables is a controversial language feature. It's well known that global variables, they cause all sorts of problems. They usually have subtle initialization semantics. Their initialization is unsafe. They break modularity. They are prone to data races. They make testing of programs more difficult, and so on. However, mainstream programming languages, they do not offer any help in improving the situation. It is a big mess. The question is, as programming language researchers, can we do better? Our work shows that it is possible to make the initialization of global variables more principled. Global variables exist in object-oriented languages in 2 forms: static fields, as in Java, and global objects, as in Scala. We base our work on global objects. As we will say, the essential complexity is the same. The problem of initialization safety can be illustrated by this simple piece of code. So here we have 2 objects, A and B. In the object A, it contains a field A, which is initialized with the field B, and vice versa. It is obvious that this piece of code is problematic. To the least, at runtime, the code will read, I initialize the field, which is always an arrow. Even worse, in the presence of concurrency, if the 2 objects they are initialized from 2 threads, concurrently, then this piece of code can lead to dead knocks. This is because in the setting of multi-threads, to initialize a global object, we have to first grab a knock on the object so that we can avoid initializing the object twice. Now suppose one thread grabs the knock on A, and the other thread grabs the knock on B, then they will wait for each other forever, a good recipe for dead knocks. We approach the problem with flow-sensitive interprocedural analysis. This way, we can relatively easily avoid reading uninitialized fields. We exclude type systems from the solution space in the beginning due to its verbosity in spite of its many advantages. The usage of static analysis raises the concern about its modularity, performance, and the explainability of error messages. We will eventually address these concerns. To deal with dead knocks, a natural idea is to require that the initialization of global objects, they form a partial order. We can use the static analysis to construct an initialization dependence graph. For example, here, it's easy for the static analysis to figure out that the object A, its initialization depends on object B and C, and B and C depends on object D. Now, if the initialization dependence graph is acyclic, we can be sure that at runtime there will be no dead knocks in initializing global objects. It seems that at this point we have solved both problem of initialization safety related to global objects. Are we done? Not really. So if we set out to enforce partial ordering using static analysis, we would soon run into a problem which we call the curse of modularity. Basically, the problem is that we cannot correctly construct the initialization dependence graph without doing whole node programmer analysis. We illustrate this point with this piece of code. So here we have three objects, object A, B, and C. In the object A, it has a mutable field F, is initialized with this function, which just returns the string hello. In the object B, it contains a field B, is initialized by calling this function F. And finally, in the object C, there is a field C, which is initialized by appending word to the field B. We might expect that the initialization dependence graph look like this. And at the runtime, we might think that the field C holds the value hello world. But that's not necessarily true. Look at this slide. The only change we did is to mutate the field F of object A at the beginning of the program. So instead of returning just the hello, it read the field C of object C. Now, suddenly, the object B, its initialization would depend on object C. So now we have a cycle in the initialization dependence graph. And at runtime, the field C, it has a value null world, because when we read this field C in the function F here, is not yet initialized. The lesson of this example is that to correctly construct the initialization dependence graph, we have to do whole program analysis. This is where we are. We wanted to use static analysis to ensure initialization safety, but we found out that we cannot avoid whole node program analysis. This is bad news because both for performance of the analysis and for explainability of error messages, we want to avoid the whole node program analysis. Facing this difficulty, we take a bold step in proposing a design principle which we call initialization time irrelevance. Roughly speaking, the principal says the state of a global object at the end of its initialization should not depend on when the object is initialized. We argue that this is a good design principle. First, it enables modular reasoning about initialization. No whole program reasoning is needed. Second, it avoids semantic surprise to programmers. Programmers in daily programming, they rarely care about when a global object is initialized. It implies that initialization time should not make a semantic difference. Otherwise, it will be a surprise to programmers. Initialization time irrelevance avoids such semantic surprises to programmers. And third, because the objects they can initialize at any time without semantic difference, it enables the compiler to perform more optimizations. And finally, as we will see, initialization time irrelevance, it allows flexible initialization patterns, which is sufficiently expressive for practical usage. Now we have the principle. The next question is how to enforce the principle. It turns out that to enforce initialization time irrelevance, it suffices to follow this rule. The rule says, during the initialization of a global object, it is forbidden to read or write the mutable state owned by another global object. A mutable state is owned by a global object if it is allocated during the initialization of that global object. So this rule suggests that we have to track ownership of mutable state in the static analysis. We illustrate this rule using this example. So here, as we can see, we define a class box which contains mutable state. In the object A, during its initialization, we create an instance of box. Therefore, this mutable state is owned by the object A. Similarly, in object B, during its initialization, we create another box. Therefore, it's owned by object B. At the next line, we can alias the box A created in object A to another field of object B. That's OK. Aliasing does not change ownership. The next line, if we try to read the mutable state of box B, that's OK, because the mutable state is owned by object B. The next line, if we try to read the mutable state of box A, that would be an error because the mutable state is owned by object A. It violates initialization time irrelevance because the mutable state here could have been changed by the main program. Initialization time irrelevance doesn't require heap separation by owners. It's perfectly defined to mix objects of different owners in the same data structure. Here is one example. We have the same box definition here. And in the object A, during its initialization, we create a mutable box, which is owned by object A. And in the object B, we create an array, a mutable array. So we can put the alias of box in this mutable array. So as you can see from this heap graph, the boxes is owned by the object B, and the box is owned by object A, and then we have a pointer from boxes to box. That's perfectly fine. And at this line, if we read the alias stored in the mutable array, that's OK, because boxes, the mutable state is owned by object B. At the last line, however, if we try to read the mutable state in the box, it will be an error because box is owned by object A. It violates initialization time irrelevance. The combination of partial ordering and initialization time irrelevance enables us to statically schedule the initialization of global objects. For example, here, the static analysis can figure out that the initialization of object B depends on A. Using this knowledge, the compiler can initialize the objects at the beginning of the program according to the topological ordering. This way, it can remove all the runtime checks about whether a global object is initialized or not. Alternatively, it may also initialize the objects at build time, as it is done in native image, an ahead-of-time compiler for Java in the GraalVM project. This way, the compiler can perform more partial evaluation optimizations. So this is where we are. With the help of initialization time irrelevance, we managed to avoid whole node program analysis. The modularity makes the analysis fast, and also the error messages, they are easier to explain. However, this solution is still not ideal. It suffers from a usability problem related to context sensitivity. We do not have time to talk about it here, so the only thing I'd like to mention is that in the paper, we introduce region context to make the analysis, in particular context sensitivity, more explainable and tunable, so that it can support complex use initialization patterns. The final solution is still not perfect in terms of modularity, in the sense that the checker would, it may analyze code across project boundaries, but nevertheless, we think that's the best solution we can achieve at the moment. Our analysis is integrated in the SPLASH'23 compiler. So as you can see here, if we feed this piece of code to the SPLASH'23 compiler, and then we will get a warning like this. As you can see, the warning reports a violation of the initialization time irrelevance. In addition to that, it shows a call trace from the root of the global object to the place where the violation happens to facilitate debugging of the problem. So that brings us to the end of the talk. Thanks for your attention. If you have questions, I'm happy to answer.
So if you have questions, please use the mic. And the next speaker.
Hi, thanks for the talk. How does your system, can you go back to the example you just showed? How does your system know that boxes 0 is a box that is an alias for the data inside the array?
Okay, so the analysis tracks all the information.
But I mean, like in Rust, for instance, right, you have lifetime parameters, and you can sort of specify in the type signature that like vector get, the lifetime of the input vector is related to the lifetime of the output reference, and that's how you know there's an aliasing relationship, and that's user configurable. And I'm wondering if this is baked into your analysis, or if I come in with a new Scala data structure, like a hash map or other things that I want to track alias relationships. Is that something I can express in user space? Or is that something that I would have to modify the analysis in order to understand like which methods coming out of my hash map produce aliases for data in the hash map?
So currently, with the analysis doesn't provide a way to specify ownership. It, by default, it assumes that if a mutability is created during the initialization of a global object, then that mutability is owned by the object. Mm-hmm. In terms of the precision of the analysis, it's possible that we introduce a region context. So the user, if they want more precision and to want more complex initialization patterns, it's possible to have more precise analysis for those, to distinguish those objects. Yeah.
Okay, thanks.
Just a very short question. How does your system interact with non-determinism in the constructors, such as depending on a global random value?
Oh, pardon?
So how does your system, your static analysis track non-determinism in the constructor of an object, like global random values that are not based on initialization order?
Yeah, good question. So we didn't mention in this talk. So non-determinism, and also if just the user in the constructor, if they call the random number generator, then it will violate this initialization time irrelevance principle. So the way we do this, because we are using the static analysis, it means we are able to track all the effects during the initialization of a global object. So it can produce warnings for those unintended effects.
Thanks.
Okay, let's thank Feng Jun again, also because this is a distinguished paper. So we move on to George, that perfect on time, well, a minute, on type-safe dynamic placement, please.
Yeah. All right, well, good morning, everyone. So this is a joint work with Pascal Weissenberger and Guido Salvaneschi. We're from the programming group at the University of St. Gallen. So the title is a bit of a mouthful, so I'll go through, first of all, telling you what the dynamic placement bit is, because I hope you all like type safety. So what is dynamic placement? When we're making distributed systems, for example, systems that support caching or geo-replication, hybrid cloud, what we care about is getting the source of the resources. So where do we put them? Where do we get them from? And these decisions are often dictated by runtime decisions, like caching, how often is a particular resource being used? Should I get it from the cache or the database? It's basically based on these sorts of conditions. And we want to encode these systems safely, which means that we would like to get the data from places we know we have a tie to or a connection with. So, okay, we looked at what kind of safety does the actual literature provide us already. There's a myriad of papers already published around architectures, multi-tier programming, placement types, choreographies. They all have one thing in common, which does not address dynamic placement, is that placement is often a static property. So once statically you have decided the placement of a resource, it is set. It cannot necessarily change anymore, which means, or not change, but you don't have uncertainty in the placement. So dynamic placement is kind of not solved using these problems. So good for us, because that's a project. And so now we want to have safe placement and dynamic placement. And this is what this paper is about, where we took the framework of placement types and we kind of tried to achieve both of these things. But I guess not everyone here is familiar with the placement types, so here's a little background. This is a particular architecture, but most importantly, this is an example architecture. So you can choose any architecture you want, but for the sake of the presentation, it's just this very simple one. There are some clients, there are some servers, but they are all tied in this particular way, which is every client is tied to a single server. Servers are tied together in any way they want, and they can connect to any client as well. But since we're programming, we cannot give this to a compiler, so there's a DSL for Scala that we've implemented in which you can specify these architectures. So that this line of code says there's a peer type called client that connects to a single server, and there's also a peer type called server that connects to a multiple client and a multiple server. This essentially encodes this architecture. But let's actually use this architecture. And for this particular program, let's decide to place a string on a client so that every client now has a string, and let's just assign it to greetings earthlings and call it message. In the type, you see that not only it's a string, but there's also this annotation that says that it is on a client. So after I compile my program, this variable will only exist on the binary that is supposed to be run by the clients. We can also do the same for functions. So this hash messages function takes a seed and is placed on a server. So it's only callable from a server. And what it does is just goes to the clients, hashes the clients using that seed. But it's a bit ambiguous where the computation should be, and we also want to make explicit what is being sent over the wire, which is why we surround that piece of code by essentially the context in which it should run, and we explicitly say which values are sent over the network. But this is essentially just placement types. It does not have dynamic placement, which is what this project is about. So how did we do this? We follow this methodology that we kind of adopted for a while about placement types, which is we take ideas from type systems and we try to put them into placement types. In 2018, with Scala Loki, we introduced these placement types as analogous to just general basic types, which is what I've shown you in the previous slides. 2019, we took the ideas from parametric polymorphism to also parameterize some architectures, and we call these polymorphic modules. And then we kept in line with this methodology to give a treatment for dynamic placement. And what you see here are some examples of dynamic placement, like database or cache. This is supposed to model stuff which is cacheable. And the solution that we took from type system is union types. And this is what this paper is about. And so the key idea is that if we take union types and we introduce union placement types, then we can statically capture placement uncertainty, which is what dynamic placement is about. So on a type level, how does it work? We introduce a type called just a type at P or Q, where P and Q are peer types. And this, again, is supposed to represent static uncertainty, because at compile time, we don't know whether this is a thing that's at P or Q. But dynamically, at runtime, we do know, because, well, it's compiled, it's happening. And so at runtime, we can eliminate some of these checks, which could be bad. And this is at the type level. At the term level, this is a particular decision we went with, which is that the inhabitants of these placement types are just remote references. We introduced them with just a keyword called remote ref. And remote is there just as a reminder that these references can cross network boundaries. So you can move around this reference, and it still points to where it's supposed to point. And as an example, this particular function reads from a cache. It takes a key and returns a pointer to some value on a cache. But itself, this functionality is located on a cache. So this is the first class from the title of the project. But this is how we introduce them, and then to eliminate them, we just use a deref as usual. But the trick here is that there's also an architecture, so we know whether we're dereferring from some peer onto some peer, so we can check whether the architecture does specify a connection between these. And we can prevent them at compile time if we know no such connection exists. To introduce the unions, we just use subsumption within the Scala DSL. In the formalism in the paper, however, we have an explicit expression that can broaden the placement of a particular reference. And so this is adapting exactly the same expression from the previous slide, except now read from cache, instead of returning a pointer to some data on a cache, it just returns one either on a database or a cache. And the elimination form of the union is just distributing the at over the union. Or in another way, just converting it to either. Then you can just use the standard library functions that are provided by Scala to deal with these two either. You can do pattern matches. You can do whatever you want with that. Right. So how did we evaluate it? Well, this is fun, but is this an actual thing? We went around to see how people usually implement dynamic placement, and we particularly found that people like to use URLs to encode dynamic placement as strings, which is not very surprising because we want to place resources, and the R in URLs is a resources, and the L is for location, right? So at least the name seems to fit. But let me show you one particular example. I don't expect you to read all this code. However, this will be the first Uppsala slide with a poem reading. And it says, the developer wrote, I don't like storage. I'm sorry, poor developer. This is all my fault. And if you take a look, there's a lot of string manipulation going on, which I guess portrays the frustration of the developer. And to James, we say, well, we're here. You don't have to suffer anymore. So how did we find this code? We went through the open source projects in F-Droid. There's about 3,000 of them. And we found that 133 use URLs for dynamic placement. But I should also say that there are many ways to encode dynamic placement, and URLs is just one of them. And we didn't look for the others. I think 133 is a good sample to show that this is a real-world problem. And some examples are in F-Droid itself. So F-Droid checks whether some repository is local or not through checking the URL of the repository to disable some sharing, because you cannot share a local repository. VLC's source code also does the same. So VLC is a media player. And Element, which is a group chat, also does this, except that they added a comment saying that if we don't do this, then this runtime exception happens. And yeah, of course, we don't like that. You can see the GitHub issue. But one particular application which we wanted to, which we focused on, is a cool podcast manager application. It's quite popular, have 500,000 downloads, 5,000 stars, 8,000 comments, so quite actively developed. And in there, AntennaPod runs on your phone. It also stores some episodes of some podcast on your local file system, and it uses your local speaker, well, the speaker of the phone, to play some of the episodes. But it could also cast to a device remotely to play the episode remotely. So what you could do is, for example, you can have your local song or episode on your local device, and since you use URLs, you can point to it using a URL. And if you tell it to play it locally, well, the speaker can access your local file system, so that's all right. Except sometimes you may want to tell it to play remotely. And we found out that the AntennaPod developers were smart enough to realize that you cannot do that, except in one particular case, because there's all of these peers that need to be coordinated to make sure that you don't play files which are not available locally, remotely, but they've missed out on one particular path. We described this path in the paper. But essentially what this allows you to do is that you can tell it to play remotely, and it just ends up playing completely the wrong file, which is, of course, a bug. So what did we do? We just took the core of AntennaPod, which is just essentially the logic of distributing and storing these applications. We rewrote them in Dino. Dino is the DSL we have. And what essentially it does is that it keeps the URL, but it also has a reference. So it can point to the correct file. And since these are remote references, they can also cross boundaries. So we don't get the previous error as before. We've also checked whether Dino introduces a big performance overhead. And we compared it with RMI, because RMI also has remote references. Dino and RMI both run on JVM. And what we implemented is a simple database cache application where you might get some sort of percentage on a cache hit or not inside of the database. And we just ran 2,500 queries. This is in red, Dino being the solid line, RMI being the dashed line, and in blue, which represent 5,000 queries, and we plotted them against time, and we see that, well, Dino does not introduce all that much runtime overhead, well, barely noticeable. That I kind of encourage you to go read the paper. It's a fun paper. There's inside it much more case studies, much more evaluations. We describe a little bit how we went around with the implementation, of course, some formalism and theorems with the proofs left to the appendix, not to the reader. All right. With that, in conclusion, the idea is that by taking ideas from type systems and applying them to placement systems, we are kind of developing richer and richer placement systems that are able to express more things. If you have questions, please go ahead and ask them.
So, again, you can use the mic. Well, in the meantime, I ask you a question.
Yeah.
Have you considered to basically introduce, how would you call it, inference so that I don't need to annotate every single thing like server infer in some of the types. You could, so that you don't have to annotate everything as server, client, cache. That you could have some inference mechanism.
So we don't do inference because the whole point of the because kind of the whole point is to make sure that
it's strong.
Yeah, the system is correct and implements what we expect it to implement. Although I think there was some work around inference,
okay.
But we just want to make sure that, for example, you don't leak onto some peer that you don't trust some other information.
So you have the types that show that it could be either there or there. But if you want to like encode in the program decisions on where to put things, how does your system interact with like these kinds of decisions? Then just the either types manual programming, or do you have any like libraries help us for also like making decision where to store something?
Not yet, but you're free to develop these libraries if you want.
Thank you.
Thanks, Ragnar.
Okay, thank you, George. And we move to secure RDTs by Sam, please.
All right, thank you. I am Sam van den Vonder, and this is joint work with my colleagues Thierry Renaud and Wolfgang de Meuter. So this work is in the context of replicated data types, and this is a type of data structure that can be replicated to multiple peers in a network. So each copy is called a replica, and via the properties of replicated data types, their contents are automatically synchronized. So you can think of them actually like Google Docs, but for general purpose data structures. Nowadays, replicated data types are powerful enough to support standard JSON objects like these, which have a key x1 and some subobject with the keys y1 and y2. And you would use replicated JSON like this in an application for two important properties, or at least properties important to me, namely offline availability and automatic merge conflict resolution. So offline availability means that when the network goes offline, each peer can independently continue to update their local object. For example, on the left, where a key x2 is added with a subfield A, and then on the right, where a key x2 is added with subfield B. And then automatic merge conflict resolution means that once the network connection is restored, then replicas will resume synchronization. And the properties of RDTs guarantee that eventually the objects converge to the same state. So in this case, merge conflicts on the key x2 may be resolved by merging the objects and keeping both keys A and B. So in this paper, we use JSON replicated data types in the domain of web applications, where synchronization is mainly between a client and server. So typically in web applications, there is a trusted application server, and the clients cannot be trusted because they can easily tamper with their local application code. So for example, in the web browser console, they can easily tamper with it, web browser extensions, user scripts, or even cracked mobile applications. So we asked the question, what if the application, as defined by the server, has data security constraints? So in the paper, we use a motivating example of a nature conservation organization like Belgium's Nature Point, which uses volunteers for the upkeep of forests and parks. And when such a nonprofit wants to find out what plant or animal species are present in a forest, then they develop a mobile app that can be used by volunteers to take pictures of plants and animals and categorize them. So the nonprofit is run entirely on volunteers, so they contact the local youth organizations, they put them into different teams and send them into the forest. And so usually this kind of crowdsourced observations includes some gamification mechanism where at the end of the day, the team with the most points wins a prize. So therefore, the company also uses an expert biologist to award points to teams based on what they cataloged. So offline availability is very important for the user experience of this application. So on a technical level, the company may choose to use replicated data types and store their application in a application state in a big JSON object. So for example, this object with the data of team blue at the top and team red at the bottom So each team has some data, like a name, some sightings. Each sighting is tagged with the key being a large number, so a timestamp, a Unix timestamp. It has some locations, species, photo, and perhaps some points and feedback awarded by a biologist. So the application also has security requirements, and I listed them here in natural language. I won't go into detail into each and every one of them, but it includes things like the red team should not be able to see the locations of the blue team sightings or vice versa. And for example, the blue team, once they have been awarded some points, they shouldn't be able to arbitrarily increase those points and so cheat at the game. So this should not be possible. I mean, this is just a didactic example, of course, but it generalizes to any situation, for example, in business applications where different users have different access to data. Now, when you want to use the current state-of-the-art in replicated data types for this kind of application, then we find that the following problems occur. So namely, replicated data leaks, data contagion, and the lack of offline policy enforcement. So replicated data leaks means that read privileges cannot be enforced, because currently with replicated data types, each user is sent a full copy of the JSON data and any updates to said data. So for example, locations will be leaked. The next problem is data contagion. So since malicious clients cannot be prevented from making local changes to the data structure, because they can bypass any local security, then whenever such malicious changes occur locally, then currently in the state-of-the-art, they are simply synchronized to the other peers, and they will gladly accept those changes as valid. So for the last problem, a developer cannot implement security checks in a typical way by contacting the application server, because then the application no longer works offline. So to counter this lack of offline availability, the clients really need to be able to locally check while they are offline what is allowed and what is not. So our proposal to solve these issues is called Secure RDTs, or SRDTs for short, and in the paper we specify them as an operational semantics engineered in PLT Redux, but by now we also have a proof of concept implementation as a wrapper for the AutoMerge library. So let's start with some base assumptions. SRDTs assume that all clients are untrusted and that there is a trusted application server which we call the leader. So typically this would be owned by the company, like the nonprofit. So compared to the state-of-the-art on data replication, we no longer allow peer-to-peer synchronization, so only between client and server, but we retain the desirable properties of offline availability and automatic merge conflict resolution. To preserve offline availability, each client must be able to locally check the security policy, but since we cannot enforce that they follow this policy, we additionally require leader-side enforcement to ensure that no data is leaked to clients and that no data is maliciously modified. So for the rest of the presentation, SRDTs can be explained in 4 steps. So first, we need some way to specify a machine-readable security policy for JSON data. Next, we need to make the security policy available offline, which we do via security policy projection. Third, we need to enforce read privileges, which we do via data projection. And so finally, we need to enforce write privileges when synchronizing changes. So the first step of the solution is for the leader to specify a security policy that grants a user access to a part of the document. And so since data in a document is stored in the leaves, which I have highlighted in yellow, and since this document is highly dynamic, so it can continuously grow or shrink, we use so-called path selectors to select potentially multiple leaves of the document at once. So path selectors are inspired by JSON path, and this is like XPath, but for JSON documents instead of XML documents. These path selectors support traversing the object based on an exact key match, a wildcard to match any key, or more programmatic predicates based on keys, one of which I will show later. So for example, the second rule of the security policy says, not of the security policy, of the motivating examples security policy, says that biologists can read the sightings of all teams. And so these 2 path selectors here, they select the fields that would correspond to this security policy. So for the first path selector, the yellow wildcard says that any key on the top level is allowed to be traversed. This must be followed by a sightings key, which is present in the object, then followed by another wildcard to traverse any sighting made by the users. And then for the top path selector, finally, the leaves which are selected by a wildcard are highlighted in blue. And then for the bottom path selector, it traverses one level deeper, namely via the location key, and it selects all of the fields highlighted in green. So using path selectors, the security requirements in natural language can be translated to code as a list of rules to allow some role read or write permissions of a particular set of fields as identified by a path selector. And by using programmatic JSON path operators on keys, the security policy can select parts of the document based on a user's properties, like, for example, being a part of Team Blue or Team Red. Now, the second step of the solution is to project the security policy in order to get a security policy excerpt for each role. So each excerpt only contains the privileges that apply to a specific user, and we do this because in some cases, even knowing that certain data exists can already be a security concern. So in the motivating example, this means that we, from the full security policy, we make two excerpts, namely for the user role and for the biologist role, and these policy excerpts can be used to send to the client to locally check whether an operation is allowed when the clients are offline. In the third step, the security policy excerpts are combined with a user environment, and this is like a set of properties about the user which are defined on the application server. It is combined with the policy excerpt to create a projection of the application data. So in the motivating example, since the blue user does not have read access to certain fields of the red the data about the red team, the striked out fields will be removed from the object before it is sent to blue users. So similarly for red users, in this case they have the same role but a different user environment, and this results in a different projection of the data where different fields are removed from the data. So data projection ensures that read privileges, that malicious reads are no longer possible based on the security policy. And finally, when users write to the data structure, this must be checked at runtime by the leader. So the workflow of an application is as follows. First, a blue user logs into the data, to the server and fetches a copy of the data, and the server responds with a policy excerpt, projected data, and the user environment. Then as long as the blue user is well behaved, they can eventually merge their changes to the server and they will accept it. When malicious users make changes, they send them to the server and the server will simply reject them. And then when a user such as the biologist merges a change, a well-behaved change, that should only be visible for members of the blue team, then of course this change is only sent to blue users and not to red users who do not have the read privileges. So since it's important that the system is actually secure, we formalized it as two languages in PLT-Redux, namely replica lang models the behavior of each client and leader lang models the behavior of the leader. So these unreadable security rules, not security rules, the inference rules and reduction rules model that behavior. So in the paper we have proofs that based on the operational semantics that the problems no longer occur there, so that it has freedom from replicated data leaks, freedom from data contagion, and the availability of offline policy enforcement. Now the formal proofs are very nice, but once we started actually executing programs using PLT-Redux, we found problems, for example, in edge cases that needed to be resolved. So we basically generate programs with lots of random data and a random security policy, and then check that all read and write access is correctly enforced. And so we repeat this for many, many objects and security policies to gain statistical confidence that the operational semantics is actually correct. And so using this technique, we were able to remove bugs from the operational semantics, one of which included a security error due to an implementation mistake on our part. So on this note, I will conclude by restating the problem. So at the start of the presentation, I explained that with state-of-the-art replicated data types, it is possible to share JSON documents between a client and server. And these have desirable properties, for me, most importantly, offline availability and automatic merge conflict resolution. But as soon as developers want to impose access control on the data, then they run into replicated data leaks, data contagion, and the lack of offline policy enforcement. But using SRDTs, replicated data leaks are solved via security policy projection and data projection. Data contagion is solved via runtime right enforcement. And the lack of offline policy enforcement is, of course, solved by making security policy excerpts available offline. So finally, if you want to experiment using SRETs, do check out the paper and our reusable artifact. Thank you.
Presentation. First off, I have a small question. Do you assume a static or a dynamic group membership?
Currently static, as in the security policy cannot change at runtime.
Okay, so why do you need the central server then?
Yeah, that's fair. Well, for one, to keep a, let's say, master copy of the data, because we assume that in a web-based setting, the clients connect to a server and then load basically the entire application state and, well, data security policy and so forth.
But then it wouldn't need to be authoritative, right?
Sorry?
It wouldn't need to have any authority then if you just only have it as a backup, right? And
well, it still needs the authority, as in it is a single source of truth, namely a peer in the network that all clients trust. As in the clients, they can't synchronize peer-to-peer currently, but they would not be able to trust each other, so at least they can contact the server to provide that trust.
okay. So it's just simpler that way to implement a central server, but in theory it would also work in a distributed scenario, right?
Yeah, so basically by doing it this way, it's extremely nice to implement applications using CRDTs and also segment the data or the CRDT based on the roles of the client. So it's a very nice way to implement it and guarantee it to be correct, no security programming mistakes and so forth.
I had the same question.
Hi, thanks for the talk. My question goes in a similar direction, and it seems to me that by using this central server, you use a lot of the benefits that CRDTs can give you in other cases, namely, for example, peer-to-peer collaboration. So that's not really possible in your setting. Is that something that you've thought about at all, or that you would like to support at some point? And do you have some ideas what the challenges there could be?
Yeah, so indeed that is something that we'd like to support, but it's extremely difficult. As in doing it completely peer-to-peer devolves into encryption, key management, and, well, trust issues essentially. We think by doing a first step with a central server, we are able to provide a level of security that might not be possible in peer-to-peer situations. Being that the security guarantees will be different if you do it peer-to-peer or if you do it via a central server. I think both approaches can exist at the same time. And so purely anecdotally, having a central server is not so academically pleasing, as in we like peer-to-peer and local first software and so forth. But in practice, there are big companies doing CRDTs in a centralized way where they explicitly do not want a central server. So Figma is the biggest example, I think, big company acquired by Adobe.
Okay, yeah, thank you.
Right.
Let's thank Sam again. Okay, and we move to Hervé Paulino, who is going to talk to us about data-centric synchronization. Made practical, interesting.
Thank you. I don't know. So my name is Hervé Paulino. I'll be presenting the paper, Autonomous Data-Centric Synchronization Made Practical, conjoint work with Anamina Matos, Ian Sedequist, Marcos Giunti, João Matos, and Antonio Ravara. We come from the University of Lisbon and the University of Lisbon. So the motivation of our work is the same of many other works on concurrent programming. So we know that concurrent code is paramount in today's software development, and also that concurrent code is difficult to write, and its correctness is very hard to assess, especially when the code scales. And so concurrent code is the source of many execution errors from data races, deadlocks, and atomicity violations. So in this paper, we promote the use of data-centric synchronization, which shifts the expression of concurrency-related constraints away from control structures, so code, to data declaration. And by this, it promotes a rather local than distributed reasoning. So the reference work in data-centric synchronization is atomic sets. In atomic sets, we have to explicitly group memory objects that share consistency properties in a set, and then reason which sets we have to take into consideration when executing an operation, namely a method. So although being a seminal work, the atomic sets, so the model is rather complex, and so it has many keywords. For instance, it also requires when using a type, to know the internal of the type. To know if the type uses an atomic set, and how this atomic set relates to the atomic set of the class we are implementing, or in the context of the method, we have to know which parameters of the method have atomic sets and how they relate also to, so which of them we have to take into consideration when executing the method. So here we propose a different approach. So we have our approach called Atomis, is type qualifier based. So we have this atomic qualifier, type qualifier, that contrary to atomic sets, it has an impact on the type. So type T and atomic T are not compatible, meaning that a value assigned to a variable of type T cannot be assigned to a variable of a type atomic T, and vice versa. And that flows upward the type tree. So if type T implements an interface I, atomic T will implement atomic I, and these are also not compatible. So besides this, we also have the notion of unit of work as atomic sets, which is a sequence of instruction whose execution must be perceived as an atomic operation. So this is Atomis. In Atomis, this translates to an excerpt, so a portion of the method body that goes from the first access to an atomic value, which is so not in calls. Atomic value, it's a value assigned to an atomic qualified variable, so an atomic, for short, an atomic variable, to the last access to an atomic value, also not in calls. So from the first access to the last access, this is a unit of work that must be executed, must be perceived as an atomic operation for the remainder of the system. So what is the programmer called to do? He has to place all the values that he wants to be accounted for in a unit of work in atomic annotated types. When it does so, if these annotations are consistent, a compilation process will generate code that's free of data races, atomicity violations, and deadlocks. So to do so, the programmer is called to annotate fields at class level. So it must annotate the fields. So it must provide atomicity information about the fields, only the fields, nothing else, in classes. So this atomicity information, so the type is left bare, means that the type is non-atomic. With atomic keyword, naturally means that is atomic. We also have this atomicity of annotation that allows for fields to share the atomicity of another. So have the atomicity of, so say that one field has the same atomicity of another field, or even of a type parameter, as we'll see further ahead. The programmer is also called to, at interface level, to say for each method which are the combinations of atomic, not atomic, that must be supported for each method parameter and return type. So the annotations are the same as above, with the exception here of all. When applied to a parameter or return type, it means that the implementation of that method must support both atomic and non-atomic for that parameter or for the return. We'll see an example ahead. So here we have a list of atomic objects. So it stores atomic objects. So when we store, the objects must be annotated with atomic. And when we retrieve, we'll also receive an atomic object. We also have here another method. This contains all that checks if the current list contains all the elements of another one given as argument. And here, it must support both atomic and non-atomic lists. Okay? Here have you an implementation. So this is a concurrent list that stores atomic objects, meaning that besides storing atomic objects, the list itself may be used concurrently, so concurrent assertions and removals, and it does so by saying that all nodes, that's here node of atomic, I'll go into that, must be accessed in units of work, and so we annotate them with this keyword atomic. So a node of atomic is, for short, a node of that stores an atomic object. Note that we don't need to annotate nothing here on the meta definitions. All the annotations will be inferred. I won't have much time to go to that, but I'll lightly or briefly explain ahead. So here are the semantics, also briefly. So as I said before, each method that accesses an atomic value, so for the first access, not in calls, to the last one, not in calls, as a unit of work. So a method that features a unit of work, this unit of work must be perceived an atomic operation, meaning that no other units of work executing may see intermediate versions of the state that's being manipulated by this method, meaning by its unit of work. So an example here, this is L1 contains L2, so checking if list L1 contains list L2, it starts by reading L1, then L1 and L2. So here the two bars, meaning that it's executing its unit of work. If concurrently we have an insertion in L1, this insertion will have naturally to wait until the first method has released the list L1. When it does so it will compete to acquire this resource, and if it does, it may execute its unit of work. Of course, others that operate over different objects may execute concurrently. So I don't have time to go also deeply into this, but we have to consider the composition of units of work. A simple example is a transfer in a bank account, which itself does not directly access atomic state, but it uses a withdrawal operation and a deposit operation that both access an atomic balance. So deposit and withdrawal will have units of work, but transfer will not, because it does not access an atomic value. Regardless, we want this operation to be atomic. For performance issues, we do not automatically compose every unit of work. What we do is, so we issue warnings for all these cases, so for the programmer to handle them, and then we have policies for more conservative to full conservative. Sorry, for less conservative to full conservative. The programmer may choose one of these policies and then even adjust the policy for individual methods by using these annotations. Unit of work, saying this method must have a unit of work and no unit of work, so this method must be an exception and not have a unit of work. So one novelty of our work is we leverage on type parameters, meaning that we can encode the atomicity of a type on a type parameter. And we do this either at class definition, here we have a class of only atomic types, or a type use where we say, for instance, that this class C extends D, and so the type parameter of D must be atomic. With this, so the type parameters now have this atomicity attribute, and this may simplify greatly the implementation of our examples. For instance, here, now we revisit the list example. We have a list of T's, and T as the type, both the type of the element and the atomicity of the element. So here, we may remove the annotations of atomic because the atomicity of the element is given by the atomicity of T. So for a list, for instance, of atomic objects, here T will be atomic. For a list of regular objects, the T won't be atomic. So if we go here now to implementations, first we have here a node of T's that will be, once again, atomic or not. And here, our list implementation will start by a base list that, besides the T element to the T type with the type of the elements, we now have a new type parameter N, where that will be used to encode the atomicity of the nodes. So N extends node, and we use this N now to declare the nodes of the list. And if N is atomic, we'll have a list of atomic nodes, and if n is not atomic, we'll have a list of non-atomic nodes. And so we can write the concurrent list simply by extended base lists saying that the nodes must be atomic and a list of sequential, so non-concurrent, with saying that node is not atomic. Now, if you want to have a concurrent list of atomic nodes, of atomic objects, sorry, we simply write it this way. So, going quickly through our compilation pipeline, we have the first case. So we have this atomic class specialization. So this atomicity property of the type parameters cannot be erased by Java's type erasure. So what we do is we have to generate a class for each of the combinations. So for this base list, we'll have 4 versions of the class. And then these 4 versions go through the rest of the pipeline. So I'll just focus on some of the stages. Here is where we infer the atomicities for the methods. So we have the notion of method variant, which is a version of a method with a combination of atomic, non-atomic for its parameters and return type. We check for each of these combinations if it's safe or if valid or not. So if it's safe, in the sense that this does not break this rule that atomic values cannot be assigned to non-atomic variables and vice versa, the ones that are deemed invalid are removed. And then we have to make sure that there are no calls, all calls to methods are calls to valid variants, and also, given that we have removed some of the variants, we have to ensure that the interfaces that the classes must implement are still implemented. So if a class, for instance, asks for a method that receives an atomic value, and the implementation makes that variant invalid, that will have to say that the interface is not being implemented. So at the end, having the type-safe code, we generate the concurrency control. So currently we use locks. We have a lock-based love injection or inference algorithm inspired here on autolocker, and we use either mutual exclusion or read-write locks. So the properties, although not presented here in the paper, we have formal implementation of the formalization of the language in Olong, what we call atomis Olong. Olong is a core language, a concurrent core language. We have formalized the inference of the qualifiers. We have type soundness mechanized in Coq. We also have behavioral soundness up to lock injection, so up to this point here, but not yet mechanized. And as I'll say later, we are working on the formalization of the lock inference. So going to numbers, also quite quickly, we have applied atomics to several use cases. Here we have some Java collections. So here are the annotations that we use. You can see that there are smaller than the original locks. More than this, the concurrency control is centralized on the data declaration, not dispersed along the code in locks and unlocks. But this number of annotations can be further decreased if you use the type parameters. So this is without type parameters, this is with type parameters. Of course, type parameters cannot be used in every case, but in this case, we can. This is the number of extra type parameters. So besides t, did we add a new type parameter, as we did for the base list with that n? So in some cases we had, in this case we hadn't. And these are besides the type parameters. Sometimes we had to use annotations that are of the type atomicity of, just to spread the atomicity of the type parameter across several fields. So say that several fields have the atomicity of that type parameter. Also have information about units of work, so we have to reason about its composition in some of the examples. So regarding compilation time, just say that currently we have so the average time is around, we'll say 5 seconds. It's under 20 seconds for so typo here, all the examples that we tested, but there's still room for optimizations, so we duplicate a lot of code and we can reduce the compilation time so we compile everything and we can reduce it. So, but nonetheless, it's compatible for use. Some runtime performance with some examples of the Java collections. You may see that we are here, so we have versions for atomic read-write and using type parameters. The impact is negligible. So we are competitive with the Java versions of, so the Java concurrent API, only when we use user exclusion. So this is given the nature of Java's read-write locks. I can discuss that offline if you wants to. Here, on this case, they use synchronized locks, and in this version of Java 17, I think, I don't know why synchronized locks performance is very bad, so we're able to be better. But if we replace the synchronized locks by locks, so the results are roughly the same. So we are competitive. We lose a little bit, but sometimes, but not that much. So to conclude, so we propose Atomis, which is a novel data-centric synchronization model with some distinct features. So it's based on this type qualifier that has impact on the types, requires only annotation of interfaces and class fields. Everything else, so local variables, so the qualification of parameters, local variables, and return times is inferred, and we generate. So if we have two versions of the same method, one that receives an atomic value, not that does not, we generate versions for both, so code for both. So it also uses Solaris type parameters to encode the atomicity on these type parameters. We have a Java implementation that shows the viability of our approach in real-life code. So, as I said, compilation time is suitable for practical use, and the runtime performance is comparable with the lock-based implementations that we have tested against. We have, so that formal definition all along that provides the framework for providing formal properties. So, as I said, we have mechanized all the type, so the inference of the qualifiers, and we have proved the type soundness. The degree of soundness is also proved, but it's not yet mechanized. We're working on this, and now we are working on the soundness of the unit of work, a lock inference algorithm. And that's it.
Hi, yeah, a couple of questions, one of which is how does this relate to the more qualifier-heavy forms of concurrent languages, things like Pony, where you have 15 different qualifiers? Have you thought about that? How does this relate to systems like Pony? Or languages like Pony?
I don't know exactly what you're... It relates in what terms?
Pony.
I don't know Pony. So
you haven't come up, okay, it's one of these things which has, you know, immutable pointers and isolated pointers and shareable pointers and this sort of thing.
Yeah, but in that kind of languages, so you have to explicitly state so what is shared and what is not. So you have so here as well. So we have to say what is atomic, and then we infer all the control.
Right, I mean, it seems you only have one particular qualifier there that doesn't constrain the heap.
So
you just have one qualifier, whether it's atomic and not atomic, and that doesn't constrain the heap, I think.
Doesn't constrain the heap?
Yeah.
Well, it does not constrain what it does, and when we execute something, so it guarantees that everything that is atomic qualified is executed in that unit of work.
Right? Yes.
But it does not constrain the heap. The only thing that what it does, you can now separate the heap on atomic values and non-atomic values. And these are not, you cannot assign values, so part of the atomic heap to the regular heap and vice versa. This is what provides you the ground or the foundation for not having atomicity violations or races.
Sure. Yeah.
So in that way, what we do is we separate the heap in two.
Yeah, I was just wondering how it related to stuff with more complicated heap topologies. And my other question was, are the sort of generic things you're using there similar to the stuff that I think Alex Pratanen did with for generic ownership in Java? It looked quite similar.
Sorry, didn't quite understand.
The way you were encoding atomicity into the type parameters in Java seems similar to the way that Alex Pratanen encoded ownership types in Java.
He also uses the type parameters?
Yeah.
Okay, didn't know.
Yeah, okay, thank you. Happy to talk to you if you catch me.
Let's thank Hervé again. Okay, we move to the last session, last talk of the session, but still interesting. So please, Christopher, your floor is yours.
Thank you. Good afternoon, everyone. Thanks for being here. My name is Chris, and today I'm going to tell you about enabling bounded verification of doubly unbounded distributed agreement-based systems via bounded regions. This is work I've done in conjunction with Niraldin Jabber and my advisor, Rupsha Samanta. Now, you all know distributed systems are infrastructure, whether it's around the house or around the world. They form a critical part of many of the facilities we use every day. Network systems are absolutely everywhere, and their correct operation is important. As such, distributed systems are attractive targets for formal verification. In particular, I want to talk to you today about automated safety verification. Safety properties require our system to never fall into certain bad states. So the system has an erroneous behavior if it can reach any such bad state. Now, ideally, we would like to have our specification and a system definition, throw them into a computer, and have it tell us, yes, this is correct, no bad states can be reached by this system. Or, no, it's not correct, because some bad state can be reached. And under some circumstances, say when the system has a finite number of processes and each of those processes is finite state, we can do that. It's very nice. Unfortunately, however, most distributed systems that we want to verify don't fall into those circumstances. As it turns out, the distributed systems we're interested in are pretty complex. For a start, we want to target systems which are built on agreement protocols like leader election and consensus. These agreement protocols have complex behaviors which are challenging to verify on their own, let alone as part of a larger system. Now, to make matters worse, these systems are often designed to scale, so we don't necessarily know how many processes the system is going to have. Say we consider a system made up of some constant number of processes, let's call that constant number C, and let M be the parameterized model composed of C identical processes all coordinating together. Now, as long as each of those processes is itself finite state, the whole system is finite state, so safety verification is decidable. We can just explore the whole state space and check if any of those reachable states are bad. However, if the number of composed processes is some arbitrary value n, this becomes what is known as the parameterized verification problem. And unfortunately, in its most general form, that's undecidable. Now, as you might imagine, undecidability poses a problem for automated verification. So we essentially want to move from being able to verify fully finite systems to being able to verify some parameterized systems automatically. And that's not an easy thing to do. But thankfully, a couple of years ago, along came a tool called Quicksilver. This is some existing work which has made some nice strides in tackling these problems. Quicksilver allows agreement protocols to be abstracted away using language-level primitives in a modeling language. And it also handles parameterized verification by implementing a cutoff reduction, which basically enables parameterized safety verification of certain types of protocols by model checking their instantiation with a finite number of processes. However, there's a big asterisk on these achievements, which is finite state processes. That's right. The individual processes in the system still have to be finite state in order for Quicksilver to be able to perform model checking. Now, this means that the processes have to have finite variable domains. And in fact, those variable domains have to be quite small if we want to fend off the state space explosion problem. So Quicksilver can verify a system with an unbounded number of processes by reducing it to a problem with a finite number of processes. But to verify doubly unbounded systems with unbounded processes and unbounded variables, we introduce Venus, which is an extension of Quicksilver, which utilizes a novel reduction to simplify this verification problem down to one that we can leverage Quicksilver's capabilities to handle. Now, to explain what Venus does, consider this process definition called consortium. It's written in Mercury, Quicksilver's DSL, and I'm going to use this as a running example. The protocol is roughly based on the arbitration mechanism for a consortium blockchain, in which a small subset of processes coordinate to make a decision for the entire system. I'm going to step through this definition and its behavior to try to help illustrate how Venus's reduction technique works. So the protocol begins with a series of declarations. These define some typed process variables and the communication events of the system, along with the associated payload domains of those events. This process definition has just one variable called data, and the rest of the process definition is really just control locations and event handlers. So if we imagine the system begins with all processes in the initial state, election. Here I've just shown 3 processes, but there could be any number. So we have these 3 identical processes, and each holds an initial default value of 1 in the data variable. Now from this location, they elect a subset of processes, the consortium, to decide on a value for all processes in the system. This particular handler says that up to 2 processes will be elected to go to a location to deliberate on what value to choose, while the rest of the processes go to another location to wait for the consortium to share that decided value. Now in the deliberate location, processes may be influenced by the environment to change their proposal value stored in that data variable. Let's say our 2 processes here get the values 9 and 7. Then, at some point, these processes engage in consensus, and they want to determine one value to agree on from the values they propose. Now, once that shared value is determined, these processes move to the decided location, and here they both hold the result of consensus, and they use a leader election protocol abstraction to choose one of the processes amongst the 2 of them to broadcast that result to the rest of the system, to the processes which are waiting in the wait location for that announcement. Here, the elected process is the red process, and the other process goes to the leader done location and stops. From the announced location, the elected process broadcasts the result of consensus to any processes in the wait location, such as this purple process here, and then it moves to leader done. And each process that receives the announcement then moves to the replica done location. Now the system is considered safe if any 2 processes in the leader done and replica done locations hold the same value in their data variables. Now, as it stands, Quicksilver can't verify this system because these variable domains and payload domains make the state space of each process unbounded. And Quicksilver requires finite state processes in order to check the conditions of its process cutoff reduction. So to reach a verification problem for which we can leverage Quicksilver, Venus has to first apply a reduction which targets the process variable domains so that we can simplify the verification problem to one involving still an arbitrary number of processes, but each of which have a small finite variable domain. At that point, we can pass it off to Quicksilver, and it'll take it from there to verify the system automatically. Now, if we take a closer look at our protocol, we can see that the data variable is only ever assigned directly from another variable or a symbolic value. We have some payload value domains of various messages, the result of consensus, and these 2 on the bottom right use this default construct, which is really just a symbolic representation of the initial value for that variable. There's no arithmetic or assignments by constants, and all that makes sense because this is really just a data coordination system. But more importantly, this system is exhibiting a property called value symmetry. This is a classical property, sometimes called data independence or scalar sets, but the basic concept is that values are distinct, but no value is treated as special. In short, the behavior of the system is invariant to permutation of the values that it's passing around. Now, another important thing to notice about the system is that when consensus takes place, the result of consensus, here denoted by this decision variable expression, is consistent among all the processes that participate in consensus. So when those processes carry that value to the decided location, there can only be a finite number of distinct values among all the processes that are there. The number of distinct values that they hold is determined by the cardinality of the consensus handler from which they get their value, which we can see here is just 1 in this case. And actually, by doing a little bit of extra analysis, we can see that all of these last 4 locations can only be accessed by processes holding a finite set of values, which is limited by the cardinality of consensus. And this forms the basis for what we've been calling a bounded region, which you can think of as just a set of locations where, one, we know that the processes there will have a finite number of distinct values among them, and which also includes all of the kind of important value comparisons across processes that we need to determine the correctness of the system. Now, outside of this region, we make no such guarantees about the number of values. There could be an arbitrary number of distinct values. But importantly, there are no comparisons across processes between the values that they hold when they're in locations outside of the bounded region. The behavior of the system doesn't depend at all on whether 2 processes which are not in the bounded region hold distinct values or the same values. That's important because that's what's going to help us kind of crush down an unbounded variable domain into something finite. And what we find actually is that when this system exhibits value symmetry, that allows us to kind of eliminate some of those unnecessary distinctness among those values while still retaining all of the relationships between data, the equalities that we need to expose any errors there might be in the system. Now conceptually, we can basically split the process state space into 2 sections. On the left, we have a region with no guarantees about the number of distinct values the processes can hold. And on the right, we have this bounded region where we can bound the number of distinct values held by any processes that are there at one time. In the unbounded region, equality between values in different processes makes no difference for the behavior of the system. So we could force processes in that region to share the same values when they might not otherwise, and verification won't be affected. This is what's going to allow us to collapse that unbounded variable domain. Now, on the other hand, inside the bounded region, distinctness of values across processes is critical to recognizing error states. So we can't collapse the values in that region to shrink the domain, but thankfully, the number of values in that region is already finite. So we can leave those alone and still get a finite variable domain in the end. So as processes move through the system, we get a trace of global states. If we look at this segment, say starting with a state where there are 2 processes, P1 and P2, in the deliberate location, P1 has the value 9 in its variable, P2 still has the initial default value. We also have a 3rd process in the wait location awaiting the decision from the other 2. And as before, we have an influence event. Process P2 gets a new value from the environment, say 7, stores it. Then P1 and P2 perform consensus. They agree on one of their values. They carry it to the decided location. After this, they're in the bounded region, so I've marked those locations in blue. And then one of them is elected to inform the other processes. In this case, it's P1 moves to announce, while P2 moves to the location later done. Finally, P1 sends the inform broadcast, and the value 9, everyone receives it, and ends up in later done and replica done. So to reduce the domain of these variables, we consider each transition in this trace. And using a mechanism called a component-wise permutation, we can map the values in the original trace into a smaller range while still preserving equality within the bounded region and consistency of values that are transmitted with these communication events. But we, in addition to that, we allow values outside the bounded region to collide with other values which are outside of the bounded region. Basically, we can permute this 9 and this 7 both to the same value of 1, because outside the bounded region, it doesn't matter if they're equal or not. And that allows us to reduce the diversity of those values. And we find that for value symmetric systems with a bounded region like this, it's always possible to compute a component-wise permutation which limits the values of the system to a finite range. So by doing this for an entire trace, we have proven that if there's an error trace in the unreduced system, then there must also be an error trace in the finite domain system. So then, thus, by the contrapositive, if there's no reachable error state in the finite domain system, then there also cannot be any reachable error state in the original system. So then, to verify this system with unbounded variable domains, it suffices to verify the system with this finite variable domain. And in this case, we found that a domain of size 3 was sufficient to prove the safety of this system. So we performed a few case studies, which I don't think I have time to go into detail on. Basically, they fall into 3 categories. Consortium, we've discussed at length. This distributed register is based on the atomic register construct from the atomics framework, and key value store is a simple key value store based on Redis. So I hope I've convinced you that by some variable domain reduction with existing process cutoff reduction, Venus is able to efficiently verify some doubly unbounded distributed agreement-based systems. And going forward, we're actively working on using these techniques to enable automated verification for progressively more general classes of systems. Thanks for your time and attention. I'm happy to take questions.
Thanks for the talk. So just to understand your problem domain, I guess, all these distributed algorithms have been extensively studied in TLA Plus and so on. And you can model check them, and furthermore, you can even apply TLAPS to actually prove them correct for any domain or any size of the domain. So how does this relate to just using the TLA model checker, for example?
Sure. If I understand correctly, you're asking about proving these results in TLA Plus for the protocols that are used inside the agreement protocols. Sure. So our approach is kind of modular in this sense. We're sort of standing on the shoulders of giants for those verified agreement protocols. You know, people did a lot of work to verify them on their own, and we said, that's wonderful. We feel no need to repeat verifying those protocols, so instead, the semantics of the modeling language essentially implement an abstraction of those protocols, sort of an over-approximation of the specific behaviors that might be implemented there, so that from some state where we're beginning consensus, we end up in a state where the value is determined and consistent amongst those participating processes, and all of the internal details of that are basically left to the proof of the correctness of that protocol. So if we want to reason about a specific protocol, we just need for the behavior of that protocol to be one of many non-deterministic behaviors that we model in our modeling language semantics. Did that answer your question?
Maybe as a quick follow-up, so why not also instantiate the application in TLA Plus on top of the protocol module?
So it's a good question. The goal of our approach is we're trying to kind of present, I guess, a unified template for expanding this decidability to like larger and larger sets of systems, which can be repurposed in a kind of a stackable way. So our hope is that as we develop more of these reductions, then you can kind of build up a lattice of systems that you can verify. And in order to verify a system which has many of these layers of complexity and unboundedness, hopefully at some point you really just need to come up with maybe one more clever reduction to kind of reduce your system into this sequence of verifiable systems and just have it take over from there. And TLA Plus is wonderful, it's very powerful, but we're hoping that we can reduce the amount of work that would be necessary to bring a new system into that set of systems we can verify automatically.
Thank you.
Thanks.
Basically, I'm looking for a quick intuition from your side. There have been a couple of papers that have been saying that like this message passing is too low level for verification, makes everything unnecessarily hard. And I'm wondering if there's something you noticed, and I'm also wondering like how deeply the message passing model is ingrained in your verification system.
Sure, thanks. It's a good question. For us at this point, the message passing it's a double-edged sword, because the more you want people to believe that your verification is, can be trusted and you've gone far enough down in the stack to uncover any interesting behaviors, the more precisely you have to model the message passing. For us, Right now, our communication model is a bit limited. We assume that it's synchronous, and the fault model is quite limited. But in kind of the spirit of what we're doing here, our hope is that in future we can add another layer on top of this, so that a parameter of the system might then be what are the exact communication semantics you're using, so that if you can step it down to something that's kind of nice and friendly, or even eliminate some transitions, you can basically simplify the verification effort and maybe even get some extra performance out of that verification.
Thank you.
Thanks.
Okay. Let's thank Christopher again. And this closes the session, but we have another very interesting session in the afternoon about distributed systems, so please join me later at room 1.
Yes, yes.
All right. Hello, everyone. Welcome to the afternoon session of Compilation and Optimization 1, for some reason. And our first presentation will be formally verifying optimizations by block simulations with Chamois and Concert by Sylvain Boulmé. So I'll let him take it away.
Thanks. So I'm Sylvain from Grenoble, and on the behalf of my co-authors, I will present some of our formally verified optimization within Chamois, an extension of the Concert compiler. So Concert is the first formally verified C compiler. It provides a proof in the Coq proof assistant that its generated assembly code behaves as the source. So the simulation is decomposed into several passes. Each pass is a transformation from one representation of the program into another one, possibly the same, but with optimizations. And each representation consists in an abstract syntax with an operational semantics given as a transition system. Because in Concert backends, all these semantics are deterministic, the correctness of a pass corresponds to a forward simulation as pictured on the slide. So within this framework, Concert provides some formally verified optimizations, such as register allocation, common sub-expression elimination, constant propagation, and a few others. But some optimizations are still missing, and generated code is slower than the one of GCC-01. So with Chamois, we try to improve this situation while remaining within this framework of forward simulations. So here is a view on Concert backend. So each box here represents a language, and each arrow represents one or several passes. So the last language is ASM. It's an abstraction axiomatized in Coq of the target assembly language. Today, I will focus on RTL, which is the last language before register allocation. It thus provides an unbound number of pseudo-registers, which is very convenient for many optimizations. So here are the main extensions provided by Chamois. So at the very end of the backend, we introduced scheduling passes for in-order pipeline processors. This is described in a previous paper. Today, I will focus on BTL, our new representation for optimizing loops with, for example, superblock scheduling, code motion, strength reduction, and so on. So while RTL represents function as a control flow graph of instructions, BTL represents them as a control flow graph of blocks, where a block is a loop-free sequence of RTL instruction with a single entry point from the other blocks. This enables to prove forward simulation between BTL programs, block step by block step. So BTL is also designed for translation validation. And here is the general architecture of a path involving BTL. So from any source S, a not trusted oracle transform it into target program T, along with ints for validation. So the formally verified validator takes three inputs, S, T, and the ints, and either it proves the simulation or it aborts the compilation with an error message. Our BTL-based optimization only use two validators. So the second one validates optimization within BTL. It uses symbolic execution and invariance provided by oracles at block entries. The first one validates translation from RTL to BTL and back. Indeed, on a translation from RTL to BTL, while selecting blocks, we may apply some code unfoldings. And conversely, when returning back to RTL, we may refold the code. So both these transformations are validated by the same validator using CFG morphism given by the oracle. So now I sketch the idea of CFG morphism on the loop unfoldings of this CFG above into one of the CFG below. So each of these CFG is actually obtained by duplicating some nodes of the source CFG. And each node has a unique label written as a source label with an index. So the CFG morphism simply consists in recovering the source label from the target label. Then the validator simply checks that the morphism preserves the successorship relation in the CFG, and of course that each node and its image contain the same instruction. This ensures a bisimilation between the two CFG. Thus, the same CFG morphism can both validate the code unfolding and the code refolding. So our main validator compares two BTL programs blocks by blocks. It ensures that each source block is simulated by the corresponding target block modulo the invariance provided by the oracle. Technically, for each block, it computes a symbolic state resulting from the symbolic execution of the block after an initialization deduced from the invariance at the block entry. Then, after normalization of the two symbolic states, it checks that they match with respect to the exit invariance. So, for example, let us schedule this function on Cortex ARM A53. So this processor has in order dual issue pipeline, and we leverage its instruction level parallelism by interleaving two successive iterations of the loop. So first, we unroll and rotate the loop body. Here, only the two main blocks are represented. So the block started at .L is a big loop body containing two iterations of the source loop. And the block at .exit simply returns the result. Then we rename with fresh names the register assigned in the first iteration. This requires to insert compensation code here in red at the first exit. Then we move the floating point operation of the first iteration below the first exit, and we interleave them with those of the second iteration. This requires to add new compensation code at the first exit. Finally, the schedule code is 30% faster than the original order here. Moreover, the schedule code simulates the code on the left here, modulo live register. In other words, for our superscheduling optimization, the invariants simply express that target live register coincide with those of the source, and that's all. As a second example, let us optimize this RISC-V code on the right, which comes from the source code on the left. So here, because because the load of immediate 7 in register X5 is loop invariant, we can anticipate it before this is code motion. Second, because on RISC-V, there are only a few addressing mode, storing at X uses 3 instructions here. But we may factorize the computation of the address here in teal color across iterations. And this is strength reduction. So here, we simply move these 3 instructions before the loop and add this compensation code, which updates the computation of the address at each iteration. Okay? So here, the invariants, they simply remind the anticipated computations on live register. And our validator prove the simulation after normalization of affine forms. So, as a conclusion, I will quickly look at Chamois performance. So here we measured the compile times of Chamois and observed that it scales on a very large benchmark. We also compare the execution times of Chamois with respect both official concert and GCC minus 01 on several architectures. So here I only show the case for RISC-V. So here each column here corresponds to a test suite. Okay, so there are several benchmarks in each test suite. The line 0 corresponds to represent the execution time of mainline concerts, and the bars they represent the gain with respect this execution time. So higher is better. So in violet, these are the gain of GCC minus 01 with respect mainline concert, and in green, this is the gain of Chamois with respect mainline concert. So Chamois is still a bit behind on RISC-V GCC minus 01, but it's closing the gap. So here is my take-home message. So translation validation is very great for formally verified compiler. First, it enables simple proofs. Second, it enables efficient oracles. And 3, the same validator may be able to prove many transformations. So this is modular design. But some key hints for validation are much easily found by oracles. So our solution is to co-design validators and oracles. Thanks for your attention.
right, if you have any questions, please come up to the mic. So one question I have is, we're closing the gap to GCC 01, but what is the gap to GCC 03? Both in terms of raw performance, but also in terms of like, what are the kinds of optimization passes that have yet, are more difficult to formally verify, that are, you're thinking about, are really critical to implement as next steps?
So, already with GCC -01, it is sometimes difficult to compete because in the intermediate representation, GCC knows much more things about the types, for example, than in concert. So, for example, the alias analysis of GCC can exploit strict aliasing, and we actually currently we cannot do this in concert because we have not kept the type information along the compilation chain. So this is an example. So after, for example, GCC -03 is very aggressive in inlining, but this is difficult to be so aggressive without taking the risk to explode the code size. So yeah, that seems tricky.
Okay, thanks. Any other questions from the audience?
Do you have any idea about the, like, would it be possible if you compare the size, not only the performance?
Sorry,
the size, the binary size.
I'm a bit deaf, so could you speak
like,
a bit?
Would it be possible that you are also competitive to GCC in terms of the final binary size instead of the performance?
Okay, so we actually currently, yeah, the size of our binary is a little bigger, yeah, maybe sometimes quite bigger than GCC -01. So currently, we do not optimize so much, just a bit. I told a bit of code refolding. Sometimes performing optimization also has the effect to reduce the code size, but currently we do not optimize the code size. So this is for future works.
So in terms of type-based alias analysis, there are a lot of problems with undefined behavior. In general, how do you, like, you can certify, or in terms of verifying correctness in cases where there's undefined behavior?
Sorry, we have to take the slides off.
So
go and swap.
Here, by definition...
Sorry, we have to swap the slides. But you can narrate.
Yeah, by definition, when you prove a forward simulation, you prove that you do not add undefined behavior. Okay?
Okay.
By definition of a forward simulation. And so we prove a forward simulation.
All right. Thank you for the questions, and let's thank our speaker. The resolution? Can you unplug and plug back to your laptop? Oh, that looks better. All right, perfect. So our next speaker is going to be Marius Müller, who's presenting Back to Direct Style, Typed and Tight. Take it away.
Thanks for the introduction. Yeah, so what is this paper about? Well, essentially, it's about the relation between, sorry? Okay, yeah. Between continuation passing style and direct style. So in the beginning, I first want to recap some key properties that are relevant here. So first, direct style. In direct style, control flow is implicit and structured. As you can see, there's a very simple program on the left. We define a function here, and when we call the function, control flow is transferred to the function, and as soon as the function is done, it's returned back to the call side. Right? This often makes it easy to read and write programs, which is why usually people tend to write programs in direct style. Moreover, in direct style, you can usually use the stack, which often enables a better runtime performance. So in contrast, here's the corresponding program in continuation passing style. As you can see, control flow now is completely explicit. The function receives as an additional parameter the current continuation, and instead of returning, the continuation is called. Moreover, instead of sequencing, we have to actually define new continuation. This little done here is just top-level continuation, and then pass this continuation to the function at the call side. So this explicit control flow often makes it much easier to optimize programs, in particular when control flow is complex. And it's easy to actually implement complex control flow in continuation passing style because we always have the continuation at hand, right? But, well, arguably, it makes programs much harder to understand, as you can already see in this little program, but it tends to get much worse as soon as programs grow bigger. Moreover, we cannot use a stack, so we often have to allocate continuation closures on the heap, which tends to result in worse runtime performance. Okay, so ideally, we would like to get the best of both worlds. So the vision for compilation actually is a workflow like this. So we have a program in direct style, and then we first translate it to CPS, then do various transformations there, and finally translate the program back to direct style to actually run it. So given that the transformations we do in continuation passing style are semantic preserving, we should, of course, obtain a semantically equivalent program in direct style. So this motivation isn't really new, and actually it already was a major motivation for the original Back to Direct Style papers by Derby and Laval back in 1992, which were the first to consider a direct style translation. In subsequent years, there were several further papers on direct style translations, in particular the ANF papers, which used the direct style transformation to actually come up with ANF. But their motivation is different. They wanted to work directly in direct style, which works well as long as control flow is trivial, right? There are several more papers, as you can see here, and these are not all. But our paper is more closely related to the original direct style papers. In contrast to them, we work in a type setting, and we consider an abstract machine semantics, and actually we prove that the machine semantics is preserved by the translations with very tight bounds, which is why the paper is called Back to Direct Style, Tight and Tight. Okay, so concretely, let's look at the initial example again. So this is the program in continuation passing style. And now we can do a transformation, say quantification, which in CPS amounts to specializing the function f here to its continuation argument at the call side, resulting in the program on the right, where f has now become a continuation, hence the name quantification. So now translating this program back to direct style actually results in the program on the right here. And as you can see, also in direct style, the function f is completely gone. So for these pure programs, this works out really nicely, and actually there is a one-to-one correspondence between direct style programs and programs in CPS. But that's not the whole story, right? In CPS, complex control flow can arise, or we can implement complex control flow. So consider this example. We again define a function, and then we define a new continuation based on the old one, and then we pass this continuation to this primitive operator. Say it's an async operator. It does not return. So it does not return in direct style either, so how can we get back to direct style here? Well, and the answer, of course, is we need control operators. So in our language, what control operators do we use? Well, the first one is this control operator called suspend, which allows us to capture the continuation, so the current stack, bind it to a variable k, and make it available in the body statement as here. So as you can see in the premise, it has a special typing judgment. So this hash here actually means that the statement S is undelimited. That is, it does not return. So the suspend sort of shifts into this undelimited world. But then, of course, we need a way to go back to the delimited world, which is why we have another operator here, which is called run, which takes a stack bound to variable k, mounts the stack, and then runs the statement as on the stack. Now, as we're in a typesetting, we can actually give a logical interpretation to these control operators. And reading this hash here as contradiction, we can see that suspend actually corresponds to double negation elimination, and run simply corresponds to cut. But that's just a little aside, right? Actually, we want to come back to compilation. So now, our goal, of course, then is to only insert these control operators where necessary. So the question is, how can we actually decide where to insert which of these control operators? And the key idea in the paper actually is to use a bottom-up translation with an additional output. You can see the CPS and the DS translations below here, so it looks a little bit difficult because it's on the whole typing judgment. But importantly here, on the left, the CPS translation has an additional input. It receives the continuation as additional input, and it's top-down. And it's sort of dual to our direct style translation. So this direct style translation is bottom-up. That is, we translate the subterms of a term recursively, and then remember in this additional output here, which is indicated with this quickly arrow here, to which continuation these translated subterms actually return. And based on that, we decide where to insert control operators. Okay, right, so now concretely, what does this look like? So here's this primitive operator async, and as I said before, it does not return. So the additional output here is just empty. Here is a call of a continuation, which we translate back to return statement. And where does it return to? Well, of course, it returns to this very continuation, which we called before. Now, as it happens, these were the subterms of this body of the function. Now we can translate back that body. And we want to translate it back to a sequencing statement where we first call this async operator. But as we can see, the async operator does not return, as you can see in the additional output here. So we have to install a control operator. And actually here we have to capture the continuation, which is why we insert a suspend, resulting in the program on the right here. So now the overall statement returns, of course, to the continuation to which the second statement returns. And finally, now that we have this, this body of the function we have seen translated back, we can actually translate back the whole function. As you can see, the body of the function returns to k, which is exactly the continuation which is the parameter of the function. So in this case, we do not need a further control operator as they line up, and so the result is the program on the right here. Now this was not too difficult, but actually there are quite a lot of edge cases, and I want to refer to the paper for that, so it's not, not a thing you want to show in a talk. Let me come back to several of the properties we've already shown in the paper. As I said, we work in a typesetting, so we show that both translations, CPS and DS translation, are typability preserving and also semantic preserving. As I said, we're very tight bound, so you can freely go forth and back. And in fact, on the pure fragment, the two machines even proceed in lockstep. So it's really a tight connection. Moreover, both translations are actually total, so they work on the whole languages, and which means you can really freely transform in both languages and then go forth and back. Moreover, they satisfy a certain kind of modularity or locality. So, for example, you can take a single function, translate to CPS, transform the body, and then translate back, and it still fits in, so the signature really stays the same. Finally, round trips are also well behaved, so when composing the two translations, they have certain properties in particular. There are one-sided syntactic inverses on the full languages, and there are even fully inverse on the pure fragment, so really an isomorphism here. Yeah, and there are, of course, several more properties, but look at the paper. So thanks for your attention.
All right. Thanks for that presentation. It was also typed and tight. Now let's get some questions from the audience.
Thanks for a good talk. So just maybe this is already in the, surely it's already in the paper, but are the two languages the same? So in particular, does that mean I don't get to iterate the CPS or iterate the direct style?
So the two functions are not the same. The DS and CPS transform, whether are they the same? No, they're not the same. So there are different languages. So one is really just CPS, and the other is direct style, which has also control operators. But you can, of course, go forth and back as you like. So you can translate to CPS and back to direct style, and then to CPS again and to direct style again.
Yeah, but I want to do CPS twice or n times.
Sorry?
Can I do CPS n times?
No. It's not. They're not really the same. Okay. So you cannot do it again. You cannot iterate the CPS translation. No.
Oh, okay. Thanks. Future work.
Yeah, future work.
Am I right that suspend is essentially for license C operator?
Sorry?
Suspend seems to be for license C operator.
Yes. It's essentially for license C operator.
Right.
Yes.
The other question I had was, you're translating into CPS in order to be able to perform various translations, and then you're able to go back again. Does that suggest an alternative whereby you could do those translations in the source language without having to go to CPS at all?
Yes, I mean, that's pretty much the original motivation for the ANF papers, right? And for pure control flow, that's actually, there's not much of a difference, right? But for complex control flow, it's often easier to do this in CPS because there's an example in the paper where you often have to somehow push continuations through control operators, which is often really difficult, right? So it's easier to do it in CPS and then translate back.
Thanks.
All right, we have time for another question if anyone has one. One thing I'm wondering is, who do you think benefits most from this paper? Like, as in, is it someone implementing a probabilistic programming language or a language of async await this is like a compilation technique they should consider? Or who do you think is the main audience?
Actually, our true motivation is to use this for the combination of algebraic effect handlers, right? Jonathan, who sits here, had this talk yesterday where we showed that we can translate algebraic effect handlers to CPS, and we would actually really like to go back to direct style. Of course, this is only a first step in the right direction here, because for that we need delimited control and should have iterated CPS, and we were thinking about this, but it's quite a bit more difficult. But yeah, that's our true motivation. But I think this should be helpful for different audiences, pretty much everything who benefits from translating to CPS.
Okay, great. Well, let's thank our speaker again. All right, and next up, we have Sarah Ashur is going to be presenting hardware-aware static optimization of hyperdimensional computations.
Yeah, thank you. I'm not Luke. Luke unfortunately got stuck in the US, so I am giving his talk. let me see. Give me a sec. Is this gonna lock? Maybe I need a mirror. Okay, let me see. I'll do mirror. I'll do mirror. Yeah, I'm working on it. Displays. Yeah, normally I don't have this issue. Yeah, I got it.
Error check.
Good, okay. Thank you for your patience. Okay, so I'm not going to state the title. Basically, there's a lot of emerging hardware technologies that promise to revolutionize computation. They offer benefits such as improved performance and energy consumption. They offer higher storage densities and faster memory access times. And at the limit, they offer new kinds of architectural capabilities, such as the ability to implement dense 3D interconnect and to have chips that are both vertically and horizontally laid out. Now, of course, these emerging hardware technologies have their growing pains. Even though they're highly promising, they're much less reliable than conventional memory and compute substrates, such as CMOS and DRAM, and they occasionally corrupt bits. These bit corruptions might arise for a variety of reasons related to fabrication, the material properties, and to sensitivities in the environment. Now, of course, the issue is when you're trying to perform classical computation on these hardware substrates, we run into problems because where corruptions occur in the program and in the program data has a substantial impact on the computed result. Namely, in classical computation, we are highly sensitive to bit corruptions if the wrong bits are corrupted in our computation, right? And so, of course, over the years, there's been a number of error mitigation techniques that have been developed to work around this problem, but these error mitigation techniques come at a cost, right? They introduce hardware complexities and hardware and software overheads that might affect the projected energy and performance benefits and might just not be implementable in this new class of technologies. So what else can you do? Well, what we can do actually is we can change how we do computation. And that is where hyperdimensional computation comes in. It is a computational paradigm that actually comes from the cognitive science community that is extremely error resilient. You can think of it as a mixture between a code and then a cognitive science primitive. The basic unit of information in hyperdimensional computation is a hypervector, which is a high-dimensional binary vector. In HD computing, information is actually evenly distributed across bits. So each bit is equally useful or useless to your computation. What this means is you can corrupt a bit at any position in your hypervector, both during compute and in storage, and it will have the same effect on your computation. The second characteristic of HD computing is that we only care about distances between vectors, namely the Hamming distance between vectors. And what that means is that you actually need many bit corruptions to occur to make two hypervectors that are far apart close together. And what that means is you end up with a highly error-resilient computing paradigm. You can implement many different things with hyperdimensional computation. We'll be focusing on data structures, hyperdimensional computing-based data structures in this talk, but you can also implement a variety of processing tasks, and at the extreme, you can actually implement machine learning models. So our work is the first static analysis-based optimizer for optimizing hyperdimensional computations to execute with acceptable accuracy on emerging hardware technologies. Right. So we present basically the first static analysis that lets you optimize these computations. Our static analysis provides accuracy guarantees over all data structures and queries that are captured by a program specification while minimizing resource usage. And as I mentioned before, it is static, which means this analysis completes in milliseconds at compile time. The second characteristic of this analysis is that it's actually hardware aware, and it's able to optimize computations to execute accurately on emerging hardware technologies. Unfortunately, I cannot really tell you about the analysis unless you understand how the computing paradigm works. So we're going to cover the computing paradigm and the analysis and the results in the next 12 minutes. So wish me luck. And the best way to cover a computing paradigm is by example. I'm going to describe how you construct a graph with hyperdimensional computing. We're going to be working with this knowledge graph data structure. It is a directed graph with labeled edges and nodes. We will refer to node labels as concepts, edge labels as relations, and edge directions as interactions. And typically what we want to do with this data structure is we want to query edges. And that's because edge queries, when you query an edge, you basically are able to ask about a relationship between concepts. For example, if you look for an edge that is flowing into the apples concept, the likes relation, you are basically asking the question, how many individuals like apples? Okay, and so to make things a little bit hairier, we want to actually execute this query on a piece of hardware that stores information in a 2-bit per cell resistive memory array. This is an information-dense emerging memory technology that is prone to error. The specific memory array that we characterize has an error rate of 2.15%. So you have a 2% chance of your bits getting corrupted. OK, so how do we encode this data structure using HD computing? Well, first off, we need to make the atomic elements of our graph. So we're going to build a set of primitives or atomics to build graphs out of. Our atomics are the set of relations, the set of edge labels, right? The set of node labels, and also the directionality of the graph, or the directionality of an edge. When an edge is incoming, it's going to be a target edge, and when an edge is outgoing, it's going to be act edge. And so edges are encoded with relative to a node. OK, so how do we do this? It's actually quite simple. We generate a random binary vector, which we're going to call an atomic hypervector for each type of node, label, and edge direction in our knowledge graph. So every primitive, every atomic in our data structure is going to become a random vector. And you might notice that if you take any two of these atomic hypervectors and you compute the Hamming distance between them, that Hamming distance will be large, which actually conceptually makes sense because the Apple node is not at all similar to the Plays edge. And so basically, similarity and dissimilarity between hypervectors capture similarities and dissimilarities in your data structure. OK, and so now we're ready to encode a data structure as a hypervector using hyperdimensional computing. And the way we're going to be doing this is we're going to be going from the bottom up. We'll construct a hypervector representation of an edge, and then we'll use the hypervector representation of edges to construct an edge set, and then finally we'll construct a graph. OK, so how do you actually encode information? Well, it's interesting. What you do in HD computing is you actually compute over your atomic hypervectors to embed information about your data structure. OK, so let's start with edges. Let's say we want to construct a label-directed edge relative to a particular node. And we're going to focus on this edge right here. So relative to the Mary node, this edge originates from the Jack node, has a likes label, and it's going to be flowing into the Mary node, so it's a target. So you can actually think of this as a tuple, target, likes, Jack, right, within the context of the Mary node. How do you encode this with HD computing? Well, what you do is you take your target, likes, and Jack atomic hypervectors, and you bind them together. A binding operation is actually a simple bitwise XOR, and what it does conceptually is it creates a hypervector that is dissimilar to its inputs. So that means if I take the HV1 hypervector and I compute the Hamming distance between that hypervector and the target atomic, the distance will be large. Same thing will hold for the likes hypervector and the Jack hypervector. OK, so basically what we do is for every edge hypervector that is connected to Mary, we're going to construct our for each edge that's connected to Mary, we're going to construct a edge hypervector that encodes the tuple, right? So we repeat this process 3 times. And now what we want to do, actually, is we want to group these edges together, right? We want to create a set of edges that contains all of the edges that are connected to the Mary node, right? And so how do we create a set of edges? What we do is we bundle the hypervectors together. A bundling operation is implemented with a bitwise majority, and what it does conceptually is it creates a hypervector that is similar to the input hypervectors, right? Which means that when you bundle together this edge hypervector, and this edge hypervector, you again get another hypervector. But if you compute the Hamming distance between HV Mary and HV1, for example, you will find the distance is small. Same thing will hold for HV2 and HV3. And the interesting thing with this property is now you can actually use the Hamming distance to perform data structure queries. So now we can, for example, test if an edge is contained within an edge set by computing the Hamming distance between the hypervector encoding of an edge and our edge set hypervector representation. If the Hamming distance is small, the edge is in the set. And if the hypervector distance is large, the edge is not in the set, right? So now we can do set membership. Now what we do is we build an edge set hypervector for each node in the graph. So we end up with this collection of hypervectors per node. And now and at this point, we basically have encoded our graph data structure, right? We have like a table of nodes and then edge sets. Now let's see what happened. Now let's walk through how you actually execute a query on this graph. Well, again, we're going to pick on this likes apples edge query. So we're going to specifically look for an edge that is flowing into Apple with a likes label So it's an incoming edge with a likes label that's flowing into Apple. And you can, of course, represent this by binding together act, likes, and Apple. So how do we do this query? We compute the Hamming distance between our query hypervector and each of the edge sets that we've just built in our data structure. And then we basically compare the Hamming distance to some distance threshold. If the distance is small, the edge is contained within the set and therefore connected to that node. And if the distance is large, then it is not contained within that set. Make sense? All right, so you might notice that I've very conveniently left out some information. You might be wondering, how do I tell if a distance is small or large? Well, the answer is you need a distance threshold, and that is another quantity you need in this computational paradigm. And the other thing I left out is I didn't tell you how big these hypervectors were, right? And so you might ask, well, how do I make these decisions? Well, the answer was, at least before our work, was that you would do dynamic tuning. So you would do a bunch of Monte Carlo simulation over a set of test inputs, and you would try to find some size and some threshold that gives you the accuracy that you want. Obviously, this approach has problems. You're not going to get any accuracy guarantees. It might not generalize well. You can, for example, construct a graph that looks very similar to the graphs you tested on, and it might give you a much worse recall accuracy. And the other issue is it's computationally intensive. Your inner loop is Monte Carlo simulation, and then you're doing a parameter search on the outer loops. Okay, so as I mentioned before, our work is the first static optimization technique that basically is a static optimizer, and what it does is it analytically derives the minimum hypervector size you need for a computation and the distance thresholds you need to use to execute your queries accurately. Okay, so now we can take a little bit of a closer look. So HEIM takes as input a specification of the program to optimize. This program specification describes the space of HD data structures to analyze and also specifies the desired query accuracies. HEIM will compute a hypervector size and a set of distance thresholds that satisfy all the query accuracy constraints in your spec. This particular constraint basically asks HEIM to make sure that edge queries on our knowledge graph data structure execute with 99% accuracy. So to be a little bit more precise, HEIM's accuracy guarantee promises that on expectation, the accuracy of each described query will converge to the accuracy specified by the most restrictive accuracy constraint describing that query. And so you basically get, it'll converge to that accuracy, right? It's not a gross over approximation or anything. And then HEIM additionally ensures that this accuracy guarantee will hold over all the queries and data structures that are described in the HEIM specification. And so, for example, in this spec, the data structure that is described is all graphs with a maximum cardinality of 4. And the kind of queries that are captured are all edge queries within this graph, within these graphs. And so basically, as long as you follow these rules, the accuracy guarantee will hold. HEIM also accepts a hardware specification, which specifies the bit error rates of different storage and compute elements in your hardware architecture. HEIM's accuracy guarantees hold in the presence of hardware error. And you might notice I also mentioned compute. You can also have error occur in your computational, during computation, and the analysis will also handle that. So it's not just on data. And so what HEIM produces as output is it analytically derives a set of optimal distance thresholds and a minimum hypervector size, and it produces those parameterizations as output. And in fact, it also produces additional hypervector sizes per query, and you can actually use these sizes to do partial computation soundly, which is pretty fun. Okay, so now we can look at the guts. Those are the inputs and the outputs to HEIM. So what do the internals of HEIM look like? So HEIM's implementation consists of an analytical model of the hypervector query Hamming distance distribution for a given data structure. And this distribution is actually parameterized over the size of your hypervector. So you can feed in different sizes, and you can figure out what your distribution of distances will look like. This analytical model is fed into an accuracy analysis, which analytically derives the query accuracies for the given analytical model. And then finally, we have an optimization algorithm that uses the accuracy analysis to find the smallest hypervector size that meets the accuracy constraints that are provided. And you can just do this, this can be done with a binary search. And so we'll take a little bit of a closer look at the analytical model. That's a lot of the technical meat of our paper. The analytical model precisely models the distribution of Hamming distance for matching data structure queries and non-matching data structure queries. The reason why we observe distance distributions is because there's non-determinism introduced when you sample those atomic hypervectors and when you introduce hardware errors. And as you might have noticed, these distributions are normally distributed. And what we do is we actually derive the closed form formulas for the mean and variance of matching and non-matching queries parameterized over hypervector size. These formulas, the structure of these formulas are of course also predicated on the expression structure. So we have many subcases that we've derived that apply to different expression patterns. And then to model hardware error, basically we compute the upper bound of the bit flip probability, and it's actually, you can very naturally fold this into the mean distance model that is used by our analysis. And then, of course, once you have that analytical model, you want to perform an accuracy analysis. We also are able to derive closed-form formulas of the expected accuracy, and then to use for this analysis. And then we're able to use the CDF of these formulae. We're able to use this formula to derive an optimal threshold. So to develop this analysis, we apply results from the theoretical cognitive science community, and we also contribute new derivations. How does HEIM perform? So we evaluate HEIM on 5 different data structures where we use 5 parameterizations for each data structure. And we compare HEIM against dynamic tuning. And we configure both approaches to try to target 99% accuracy on the query, on being able to recover information. So comparing runtimes, HEIM runs in milliseconds and is 2 to 5 times orders of magnitude faster than dynamic tuning. And as you can see, the runtime is flat. So it does not depend on the data structure size, which you would expect because these are all closed-form statistical models. HEIM also is able to much more reliably give you the accuracy that you want. To evaluate this, we sampled 100 random data structures that were conformed to spec, and we evaluated dynamic tuning and HEIM on these data structures. As you can see, all of the HEIM data structures, which are in blue, are above the dotted line, which means they satisfy the accuracy requirement. And then, as you can see, the dynamic tuning is under the gray line in a lot of these benchmarks, which means that once you try to generalize it to other data, generalize the parameterization to other data structures, you no longer get accurate recall. And you can see in some cases you never actually meet the accuracy that you want. One more point I'd like to make. One of the cool things with this sort of analysis is that you can actually do applications to devices co-optimization. And this lets you do ISO accuracy analyses of different hardware technologies. For example, we evaluated whether it's ever beneficial to use 3 bits per cell memory versus 2 bits per cell memory versus conventional memory. And we found that at ISO accuracy, 3 bits per cell resistive RAM is worse than DRAM. But 2 bits per cell ReRAM is actually, the storage benefits are not eclipsed, right, by the amount of additional bits you have to consume to retain a specific accuracy requirement. So anyway, the neat thing here is you can do systematic applications to devices analysis, which is typically very, very hard to do with classical programs. And that is it. I will take questions.
Yeah, questions? Please represent your question as a bit vector.
Will be difficult. Thanks a lot. I found the maps very cool. I wonder if you have tried to benchmark this kind of hyperdimensional computations against a traditional approach, because it's not totally obvious that good old error correcting code with known algorithm in the task vectors.
So you're asking about the comparison with ECC, is that right? Like error correcting codes. Okay, so yeah, the thing with ECC is that it works when you want to just store data, right? You encode your data, you store it, and then you decode it. But then you still have the decoding operation. Your computational path still has to be accurate, right? With this, you never actually decode your data. So you can actually just keep operating over the hypervectors on the data path and experience corruptions and be fine. Does that make sense? So it's a little bit different, but actually...
I was thinking runtime. How does it compare in terms of performance?
Okay, yeah, I mean, we might have to take this question offline because I think the next speaker has to go up, but, right?
You just take the laptop off and then...
Okay, got it. Yeah, so to do that, you'd have to compare ECC and redundant computation, right? I don't think anyone's actually done this comparison. I mean, I should also mention this computing paradigm has only been used practically for the past 2 years. So there's obviously a lot of work still to do with these comparison points. I would also like to add that data structures are not really where we want to target our end goal, right? We want to actually target some of the ML use cases. So, okay. And I'll take questions after the session.
All right, let's thank our speaker one more time. All right, and next up we have rapid region-based pointer disambiguation presented by Khushbu Chitre.
Okay, so good afternoon, everyone. I'm Khushbu Chitre. I'm now going to present rapid region-based pointer disambiguation, which is a joint work with Dr. Piyush Kedia and Dr. Rahul Purandre. So consider the code snippet in box 1, which is a simple code to add elements of 2 arrays and store the result in a separate array. Assuming the memory location pointed by A never overlaps with B, C, and size, the loop can be vectorized as shown in green in box 2. In the vectorized version, the hardware can do 4 computations parallelly instead of 1 sequential computations in the original loop. Therefore, the vectorized version of the loop is very efficient. However, it is hard to tell statically whether A, B, C, and size overlap because it depends on the arguments of foo. In other words, sometimes they can overlap and sometimes they might not. Thus, a dynamic check is always needed. However, the major challenge is to implement these checks efficiently. This is the problem that we are trying to solve in this work. So our approach can disambiguate 2 pointers only if they belong to different objects. So at the high level, we use the profiler to identify the pointers that require the dynamic check, and the output of the profiler is shown in box 3 here. During the execution, we ensure that the pointers that require dynamic checks are at least the distance apart as shown in box 4. Therefore, our dynamic checks simply verify whether the pointers are at least the distance apart or not. This can be implemented very efficiently, and we named our approach RAPID. So we will use this example to demonstrate our approach in the coming slides. Here, A, B, C are allocated using malloc, and size is a stack allocation. So if 2 pointers require a dynamic check, we ensure that they are at least the distance apart. And to do that, we need to identify their allocation sites. So we rely on a profiler to identify those allocation sites. So as shown on this slide, the profiler generates all the pointer pairs that needs to be placed at least the distance apart. So in this case, we need to ensure that AB, AC, and A size are at least the distance apart. So our region-based allocator API, rmalloc, takes additional parameter to make the pointers at least the distance apart. So 2 pointers belonging to different regions are always the distance apart, and by default, the stack allocation is always from region 0. So allocating regions 1, 2, and 3 to ABC will ensure that all the pointer pairs that require a dynamic checks are placed at least the distance apart. So once we allocate them in different regions, we can optimize the loop using a dynamic check, which simply verifies that all these pointer pairs are placed at least the distance apart. Now the profile phase is used to capture the allocation sites corresponding to the pointer pairs that require a dynamic check. Thus our profile phase transforms the main function as follows. So all the calls to malloc are replaced with malloc prof along with the stack allocations. So this malloc profs take allocation site of the object as an additional parameter. So for example, at line number 11, we pass the allocation site of A to malloc prof because it is the allocation site which represents A. Now malloc prof allocates 8 bytes in addition to the allocation size, where it stores the allocation site of that object. So for example, in this case, 11 is stored at the initial 8 bytes of where we are allocating A. So if the dynamic checks hold in the profile phase, we log the allocation site stored by malloc prof corresponding to the pointer pairs that requires a dynamic check. Now this ensures that the pointer pairs are at least the distance apart at allocation. Now during the profile phase, the dynamic checks verify whether A and B belong to different objects. Since A and B could also be an internal address of the same object, we use the starting address of the object to disambiguate the pointers. Now, if A and B point to the same object, their starting address will be the same. Now, in the profile phase, if the starting addresses of the objects in a dynamic check are different, the pointers are considered to be non-overlapping, and this log function will log those pointer pairs so that we can ensure that they are placed at least the distance apart. Now, because additional regions add overheads, our first goal is to minimize the number of regions. The second problem arises when the allocation sites of the conflicting pointer pairs are the same. For example, the allocation sites could be inside a loop. So in that case, we cannot assign unique regions to all the allocations. Now we minimize the number of regions by using a graph coloring algorithm. Let's now discuss that in detail. So to minimize the number of regions, we first build an interference graph in which two nodes are connected if they belong to if they don't belong to the same region. That is, they are placed at least d distance apart. So all the pointer pairs logged by the profiler should not belong to the same region, and thus there should be an edge between those pointer pairs. So in this graph, AB, AC, and A size, all of them should not belong to the same region, so that's why we have the edges between all of these pointer pairs. Now, the problem of minimizing the number of regions is the same as the problem of finding the minimum number of colors to color this graph when two adjacent nodes in the graph cannot have the same color. We use an approximation graph coloring algorithm to assign regions to the allocation sites. So for this graph, the algorithm concludes that we can color this graph using two colors. So we allocate A from region 1, and the other allocations can be done from region 0. Now, this is the final code that uses the regions computed using the graph coloring algorithm. Now, notice that we don't replace the allocations to B, C, and size, since they are the default allocation is always done from region 0. So now AB, AC, and A size belong to different regions, and thus the dynamic checks at line 2 will always succeed during the actual execution. Now we deal with our second challenge of handling memory allocations inside a loop using a round-robin approach. Let's now discuss this in detail. So this example shows an alternative implementation of main, in which the allocations to A, B, C are replaced with array 0, 1, and 2, and they are allocated at the same allocation site, which is at line number 13. Now, we can't change the allocation of A, which is now array 0, to allocate it from region 1, because in that case, array 1 and 2 will also be allocated from region 1, which was supposed to be allocated from region 0, and thus the dynamic checks will fail. So to counter this, we used an approach that allocates objects inside the loop from a set of regions in a round-robin manner. So for example, the set of regions that are allocated to this loop are from start region to end region minus 1. Here, cur region represents the next allocation that should be done inside the loop. So initially, cur region points to start region. Then it moves to start region plus 1, then plus 2, and then plus 3, and finally to end region minus 1. So when all the regions are exhausted, we come back to start region. Now, in the non-round-robin approach, the dynamic checks might have failed even if the actual objects didn't overlap, but they don't fail with the round-robin approach. With higher number of regions, the likelihood of dynamic check failure reduces. However, increasing the number of regions might also increase the overhead of our approach. But in our experiments, we found that with 16 regions, the dynamic checks never failed, even for significantly large benchmarks. Now let's take a look at how this region-based allocation works. A region contains a list of segments. The size of every segment is 4 GB, and here 4 GB is the value of D that we used in our dynamic checks. D could also be any size with a power of 2. So in our approach, D is also the maximum object size. Now a segment is further aligned to 4 GB. Then each segment belongs to only one region. This ensures that 2 pointers that belong to different region must belong to different segments. Now, because an object always fits within a segment, if two objects belong to different regions, they can't overlap. Because the starting addresses of all segments are 4 GB aligned, two addresses belong to different segments if the top 32-bit values in those addresses differs. Thus, the dynamic checks simply check if the top 32 bits in the pointer pairs are different. Now, this slide shows our actual dynamic checks, where the condition A XOR B greater than 4 GB is true if top 32 bits in A and B are different. Notice that our dynamic checks are very efficient and it doesn't require any memory access. A prior work named Scout is based on the idea of constraining the object size and alignment of every object to the nearest power of 2. At runtime, it can compute the alignment in one memory access. Using the alignment, an object starting address can be computed without any memory access. The pointer pairs are disambiguated using the starting addresses. However, Scout constrains the size and alignment of all objects irrespective of the fact that whether they are accessed inside the optimized loop. Rapid, on the other hand, constrains the selected memory locations. Consequently, the CPU and memory overheads of Scout's allocators are high. Scout's dynamic checks also require memory access, whereas Rapid's dynamic checks don't. Scout thus performs poorly for memory-intensive benchmarks. Despite its efficient dynamic checks, Scout's overheads reduce its overall gains. Then we estimated our performance benefits obtained by Polybench and spec benchmarks when compiled with our approach, and we also compared our results with Scout. So our approach required a maximum of 4 regions when memory allocations inside loops were not handled. And 32 regions were sufficient when memory allocations inside loops were handled, triggering our round-robin approach. We found that only 3 of the 12 spec benchmarks have memory allocations inside the loops. Now, in all the graphs, the blue line represents the results for Rapid, whereas the red line represents the results for Scout. This graph shows the CPU overheads of Scouts and Rapid's allocators. For overhead, negative value indicates an improvement. The maximum CPU overhead of Scout was observed to be 8.36%, while for Rapid, with 32 regions, it was only 0.46%. This graph shows the memory overhead of Scouts and Rapid's allocator. The maximum memory overhead of Scout was observed to be 34.89%, while for Rapid with 32 regions, it was only 6.96%. With multiple regions, our allocator needs to allocate at least one segment for each allocated region. Multiple segments end up adding additional overhead for some of the benchmarks. This graph shows the performance benefits, including the allocator's overhead for Scout and Rapid. In the upcoming graphs, the positive numbers represent an improvement. Here, Scout showed positive performance improvement only for 5 out of 12 spec benchmarks. For Rapid, all 12 benchmarks showed a positive performance improvement with a maximum of 3.84% improvement. Apart from X264 benchmark, Rapid performed either better or similar to Scout. For X264 benchmark, Scout performed better because the Scout's modified allocator performs better than native for this benchmark. This graph shows the performance benefits, excluding the allocator's overhead, for both the approaches. So both Scout and Rapid improved the performance of all 12 benchmarks with a maximum improvement of 1.88% for Rapid. For some benchmarks, our tool performs better than Scout because the overhead of our dynamic approach are lower than Scout. Now, this graph shows the performance benefits for Scout and Rapid for Polybench benchmarks. We observed that performance benefits for most of the Polybench benchmarks were similar to those of Scout. The memory allocations in these benchmarks was very low. Thus, no significant performance difference can be concluded for Scout and Rapid for these benchmarks. So in conclusion, we observed that RAPID improved the performance of all 12 spec benchmarks. Therefore, we can conclude that RAPID can be used with real-world applications due to its efficient dynamic checks and low allocator overhead. It allows the compiler to enable missed optimization opportunities. Thank you. I'm happy to take questions now.
All right, any questions, come to the front.
Hello. Hi. Can you say a little more about how performance changes if you picked a bad number of regions?
If you, sorry?
The number of regions makes a big difference for the performance, correct?
Yeah, so we tried with the different number of regions increase for that round robin approach up till 256. So mostly the CPU overhead was approximately around 0.6%. So maximum was around 0.6%. But memory overhead obviously increased because of the fact that now the number of segments required are more. So mostly CPU overhead, I can conclude that mostly CPU overhead was not that much.
Okay, and then do you always just pick the maximum number of regions that you can support? Or how would I, as a programmer, pick the regions?
So that depends on the fact that, I mean, if the dynamic checks, the number of regions required, you can say the point or the number of regions where the dynamic check failure is like, I mean, no dynamic check fails, then in that case, I think that is the best choice to pick the number of regions. Okay. Otherwise, it depends on the user if they want to pick more number. But then again, the problem is it might increase the memory overhead.
One question I have is the effect, did you look at the effect on the binary size of adding these conditions? Does it substantively change the final binary from having the extra branch in the generated code?
Yeah, we saw that. I mean, the overall the code size, from the perspective of code size, but maximum, as far as I remember, it was like there was only one benchmark in which there was only like 3% increase in the code size. Yeah. So.
Got it. Okay. Thanks. Okay. All right. Well, let's thank our speaker one more time.
Thank you.
And to round out the session, we have Jiangyi Liu, who's going to be presenting automated ambiguity detection in layout-sensitive grammars.
Hi, everyone. It's my honor to have the chance to give the talk here. My name is Jiangyi Liu, and I collaborated with Fengmin Pao Zhu on this paper. I'm a first-year PhD student in the University of Wisconsin-Madison. Since I was an undergraduate student in Tsinghua University, I've been working on this project with focuses on aiding layout-sensitive grammar design. I've talked enough about myself, so let's start by having a look at the layout-sensitive grammars. So what are layout-sensitive grammars? By definition, it's a type of grammar where indentations and white spaces affect the parsing process. The layout in its name means positioning of the tokens, which depends on the white space symbols. This is quite different from the context-free grammars, where white spaces are discarded in the tokenization phase. The following Python program illustrates how layout affects parsing. On the left side, only the second print statement is executed, while on the right side, both prints are not executed since they both belong to the if body whose guard condition is false. Python is a language defined with layout-sensitive grammars, and therefore, indentations play a big role in the semantics of those programs. Layout-sensitive grammars have a wide application. It has been used in many modern programming languages, including Haskell, Python, and F#. What's more, newer versions of existing languages, like Scala 3, are also trying to integrate this feature. However, not all programming languages are layout-sensitive. There are many of them that can be expressed solely with context-free grammars. So why using this type of grammar? Shouldn't context-free grammars be enough to express the programming languages? A main reason would be that it encourages writing elegant and stylized programs. In fact, one reason why Python chose this type of grammar is that it enhances readability. As in Zen of Python, we have readability counts. Python is known for its bracket-free and semicolon-free coding style. Many Python programmers are so into this style that they try to apply such a style to other languages, and here's a case of this. Since this programmer hits the semicolons here, they moved those disturbing symbols to the end of each line. It is so unnatural that this case seems a little bit silly. However, that programmer would certainly love Scala 3. The Java code can be rewritten into the following Scala code. Scala used to do not support layout-sensitive grammars, but it supports using indentation to denote the control flow structures now. It looks much cleaner and easier to read, isn't it? Suppose that you are trying to build your own programming language that uses layout-sensitive grammars. This is indeed favorable given that there's already languages like Scala 3 is already doing so. When it comes to such a serious use, we have to take possible ambiguity into consideration. That is because in most cases, you don't want the programs in your language to be ambiguous, since it makes those programs no longer reliable. Only if you rule out the ambiguous grammars can programs become solid and clear. But how can we check if a grammar is ambiguous? It might be tempting to try identifying and eliminating ambiguity manually, but it's really hard to do so. Here, we present a fragment of layout-sensitive grammar used to describe the statement blocks. There are two production rules out there, and the block symbol is the star symbol. Note that we extended the EBNF to include the annotations like this little double pipe symbol that acts as the layout constraints. Oh, like this? Okay. So the second rule is rather straightforward. A statement can either be a not token or a do token followed by another block. The first rule, however, includes a layout constraint, which we call aligned claim class. To begin with, it's a claim class, which means the terms within should occur one or more times. What's more, it requires every line to be aligned. That is starting from the same column as shown in this graph. So how many of you think this grammar is ambiguous? If you think so, can you provide a counterexample? Please raise your hands if you think so. Okay, maybe many of you have guessed that it's an ambiguous grammar. Here we have a sentence which acts as a counterexample. Below it is what the tokenizer generates for the layout-sensitive parsers. Note that the tokenizer's output now contains the line and column numbers that may be used by the parser. We also listed out the two parse trees here. In the first tree, both null ops belong to the do block. However, in the second tree, only the first null op token belongs to the do block. In this corner case, the cause of the ambiguity is the fact that all tokens are aligned with each other. So what did we learn from this example? Manually determining ambiguity is rather hard, and we should switch to automated ways instead. However, an instant question would be that, isn't the ambiguity of grammars undecidable? The answer is a big yes, and we should find an incomplete but useful way instead. Let's introduce bounded ambiguity checking, which is such an incomplete but useful way. It's a weaker notion of standard ambiguity, which checks that there's no ambiguous sentence under a certain length k. The idea of bounded ambiguity checking comes from Isaacsen's work on CFG ambiguity detection. The next question would be, how do we solve the weekend problem? Isaacsen then created an encoding called BAMB, which we listed here, and proved in their paper that it is equivalent to bounded ambiguity. We first started by directly extending the BAMB encoding to include the layout constraints, like the line and column relations, and switched to the use of SMT solvers instead. But then we found that a direct extension of their method would be not enough. We started by trying to formalize the direct extension encoding with the cock-proof assistant. However, we failed to prove the soundness of their work in cock. By inspecting the failing proof goals, we determined that the direct extension to be unsound. To bridge the gap, we strengthened it into a new concept called local ambiguity. It repaired the unsoundness of the BAMB encoding on layout-sensitive grammars by introducing extra conditions and makes the encoding sound again. Starting from the concept of local ambiguity, we created the following benchmark. the following framework, sorry. To begin with, we created an ambiguity checker in Python, which first encodes the local ambiguity condition in SMT formula, and then invokes the Z3 solver to check if there's an ambiguous sentence within the given length bound K. We've also formalized our theory in Coq, and proved the equivalence between local ambiguity and the standard bounded ambiguity here. We also showed in Coq that the SMT encoding is analogous to the local ambiguity condition. In the rest of the talk, we focus on how we achieved the local ambiguity condition here. For the other parts, you can refer to the paper for details. Recall that we started from the previous work by Isaacson and strengthened their encoding to adapt to layout-sensitive grammars. We've already mentioned that BAMB alone is not enough for layout-sensitive grammars. To go into more details, let's first illustrate Isaacson's BAMB condition with the following graph. BAMB tries to find the two subtrees with roots labeled A that differs on the first level. In short, BAMB finds ambiguous subtrees instead of full ambiguous trees on the right side. After those subtrees on the left side are constructed by the encoding, the full parse tree wouldn't need to be produced from those two subtrees T1 and T2. To recover the complete ambiguous sentence, we need to complete the missing parts like the TL and the TR subtrees. Isaacson has shown in their paper that such a completion can always be done for context-free grammars. However, this doesn't apply to layout-sensitive ones. So let's start with an example grammar here. This grammar is not ambiguous, and it has 6 production rules and starts with the symbol S. The rule S to A requires that all tokens derived from A lie on the same line. A derives to B1 and B2. B1 and B1 contains an alignment restriction. Alignment here means that the first token on both sides should lie on the same column. Intuitively speaking, B1 can only produce a multi-line sentence. However, given that S only permits all tokens to be on the same line, B1 can be seen as actually a disabled production rule that will never apply. Hence, the grammar can never be ambiguous. However, the following sentence satisfies the BAMB encoding. It contains 2 Cs on the same column of 2 lines. By inspecting the BAMB encoding, we found out that it detected the ambiguous subtrees T1 and T2, which are both valid. Hence, it concludes the ambiguity of this grammar. However, when we try to recover the full parse tree from the subtrees, we found out that the full trees are actually invalid. This is because the rule starting from B1 should never be used, as it's in conflict with the first production rule. Therefore, this example is a false positive for ambiguity. So why this can happen with layout-sensitive grammars? If we only focus on the subtrees, even if we find ambiguous ones, we cannot be certain that those subtrees can be extended into a complete parse tree. Like shown in the graph, in the previous graph for BAMB, the existing complete trees may not be valid at all. But recall that Isaacson has proved in their papers that for CFGs we can always do such an extension, since there won't be things like the layout constraints that stands out in the way. To resolve this, we need to drop the subtrees that do not correspond to the full parse trees. This can be seen as the subtree being unreachable from the star symbol S, and those unreachable ones should be dropped in the encoding to ensure its soundness. So we start by reviewing the classic reachability definition on context-free grammars. A non-terminal X is reachable in the context-free grammar if there exists a derivation starts from S that produces it. Note that when we define reachability here for context-free grammars, we do not consider specific sentence W. That is because reachability for context-free grammars can be decided by the grammar structure alone. But that's not the case for layout-sensitive grammars, because whether a layout predicate is satisfied actually depends on the sentence that is currently being parsed. I'll intuitively explain how we adapt reachability to the layout-sensitive grammars. Suppose that we already have a parse tree on the left-hand side, starting from the non-terminal A and derives the sentence W. We want to know if this parse tree corresponds to a complete parse tree that starts from the star symbol S. If we come to the figure here, we can see that it corresponds to whether we can find the red parse, like TL and TR, and the parse above it, the one starting from S, that completes the subtree T. If so, there would exist a path that goes from S to A on the full parse tree. Hence, we have the name reachability here. This wouldn't be needed for CFGs, since the subtree in CFG can always be trivially completed. However, here, we have already shown that for layout-sensitive grammars, the layout constraint on the path from S to A can actually make the completed parse tree invalid if any of the constraints on that path is not satisfied. With the reachability condition in hand, we can actually define our own equivalent notion for ambiguity. Local ambiguity is defined as the conjunction of BMB and reachability. We then proved in Coq that the local ambiguity condition is an equivalent condition to bounded ambiguity. Now that we have local ambiguity, we can translate that into SMT formula. It discusses whether the ambiguous sentence is empty and respectively encodes the BMB and the reachability conditions for each case. We've also proved the correctness of the given encoding and showing its bounded soundness and completeness. Soundness says that any sentence defined is indeed ambiguous, while completeness says that if there exists an ambiguous sentence of a certainness k, then the SMT formula phi k is satisfiable. What are the take-home messages from this talk? To begin with, ambiguity is quite important in language design. Sometimes people can actually avoid ambiguity detection by choosing the correct fragment like LL or LR grammars. When this is not possible, as in the case of layout-sensitive grammars, we have to have a way of automatically detect the ambiguity. The second point is about the proof assistance. They are actually quite useful and can surely help you develop a robust theory when you are working with SMT or set solvers. Last but not least, SMT solvers can also be applied to formal language research, as we've shown in our work, other than its well-known use in software analysis. You should read the paper if you're interested in the details. We also have our benchmark data in the paper. Please scan the QR code to download a copy. Thank you all for your attention. If you have any questions, feel free to ask me.
All right, any questions for our speaker? Come up to the mic. I will start. So you showed two primitives that are supported in your grammar of like all tokens must be on the same line and then tokens must be along the same column.
Let me turn to that slide first.
Sure. And I'm wondering, I guess, how expressive these primitives are in capturing the space of layout-sensitive languages. Like I know, for instance, in Markdown, they have cases where you can indent a certain amount, and then the next line must indent exactly that much, or sometimes a little bit more, a little bit less. Like, do you have a sense of how expressive this is? Can this capture kind of most layout-sensitive designs that exist in the world, or would you need more primitives for that?
So your question is about whether it's possible to extend the primitives to adapt to more layout-sensitive languages. And the answer is another big yes, because we actually encoded those layout constraints with the first-order logic formulas. So in theory, you can actually edit our tool to implement your own layout constraints, so long as it can be expressed with SMT formulas.
Okay, great. Any other questions? All right, well then let's thank our speaker and grab some coffee.
Thank you so much.
Oh, it's already.
So your first one? Yeah, you can stand here. Yeah, you can stand here. I think here is better.
Here. Hello, everyone.
I will check.
Good afternoon. Welcome to the session on refactoring. I'm Gautam Kaki. I'm the session chair. So our first talk is on aliasing limits on translating C to safe Rust. The speaker is Peter Boyland. Thank you.
Hello, everyone. I'm here to present our paper. Can you put up the slides?
It's Mac.
All right. Okay, so slides are up. I will be presenting this paper. Unfortunately, Mehmet, the first author, was not able to make it due to visa issues, so I'll be presenting this. So I'm going to go through the motivation really quickly. C is dangerously memory unsafe. We look at the CVEs. A lot of them have to do with memory unsafety. Rust isn't. However, it's still not very used, and in particular, a lot of the code that exists is still in C or C++. So I'm going to go through some previous work, which was going towards addressing this problem, and then I'm going to talk about our contributions. So because C is dangerously unsafe, we might think, OK, we can translate our C into the Rust code, and this will result in the code bases becoming a lot safer. And in fact, there are already some projects working on this. So one of the major groups doing this is the C to Rust project. And you can see the diagram they have here. So they take the unsafe C, they use a transpiler, turn it into unsafe Rust, and then the idea is that the programmer intervenes and repeatedly makes it safer until eventually you can compare it with the original code. You have hopefully some idiomatic Rust. And some of the key traits of this is that this transpilation process preserves the semantics. So the program will do the same thing after being transpiled as it did originally. And the structure is also roughly preserved. However, because it transpiles into unsafe Rust, you end up with a lot of use of the unsafe keyword. So Rust's escape hatch from the strong safety guarantees. And in particular, it uses these raw pointers, which these raw pointers can be used pretty much the way that normal C pointers can be used, which is, in fact, pretty unsafe. So if we want to automate the process of turning C into safe Rust, we have some issues. So one of the issues is that the type system isn't officially formalized. So there's a lot of good different attempts with different goals. So some of them are very focused on security and hardware. Some of them are more focused on the interesting features of the type system. But none of these are official, and none of them are made specifically for our process of coming from C. So in our previous work, we took this Rust code, and we took advantage of the compiler, which is effectively the stands in for the formalization of the type system. And this process, we would assume that the code, we would make the optimistic assumption that all the pointers could be made into references. And then we would use the compiler as an oracle to repeatedly take these references, and whenever it doesn't work, whenever there's some problem, we turn them back down into raw pointers. And out of the pointers that we deem eligible, a large majority of them are able to be made safe. However, this eligibility sort of hides a bit. So any pointers where pointer arithmetic is done on them, any pointers with casting between different types of pointers, calls to external functions, and really importantly, all the pointers that stem from these issues are not eligible. And so we have a question. If we didn't have any of those problems, how many pointers could Laertes make unsafe if we only had to deal with lifetimes? And the answer is actually somewhat surprising. So the way that we do this is we need to simulate a solution instead of actually solving it, because we don't have solutions for these translation problems, and we can imagine they're pretty difficult to do. So we're going to make a modified program that doesn't have any of these issues, which doesn't have pointer arithmetic, external functions, and so on, and we can analyze that one instead. So the key things that we have to preserve is, because we want to focus on lifetimes, we need to make sure that the lifetimes of the variables, their aliasing information, what they are owned by, has to stay the same. However, we can change quite a bit. We can change the dynamic semantics completely. So if you see here, our x.offset I is translated into ix, which just doesn't do any arithmetic whatsoever. So this dynamic semantics is totally changed, but the type information, the ownership is the same. So we use this, and this drastically increases the number of eligible pointers. So we go from 641 to over 8,000. And in addition, we're also able to increase the number of pointers we're able to make safe, also substantially. So you can see this here. However, you'll notice that the amount that these went up is different from each other. So we go from 72% to 12%. The 72% is based on a different analysis of the pointers. So there's a question, why is this number much lower than we might hope for it to be? And the answer turns out to be aliasing, which I'm going to go into now. So we have these, the answer is that as we increase the number of eligible pointers, we also increase the size of the sets of pointers, which are mutually contaminating, where a problem with one of them causes a problem in all of them. So if we take the TMUX benchmark that we have, when we analyze it, we find that some pointers, in particular 15% of them, as you can see on this graph, don't affect any other pointers. So if one of them is contaminated, then it doesn't spread at all. However, 85% of the pointers here affect almost 4,000 of them, which is most of them here. So one error here, one necessary raw pointer is going to cause all of them to be raw pointers. And this effectively answers our question. The larger our aliasing classes are, the higher the chance that one of the pointers is unsafe. And then if one of the pointers is unsafe, the worse the effect is. So increasing the size makes it extremely likely that we're going to have a problem. You can see here for the other benchmarks, so previously I was showing TMUX, but the parts I've highlighted here show the largest equivalence classes in those individual benchmarks. And remember, any error in any of these equivalence classes is going to contaminate the whole all of those pointers. So we can ask the question, well, what if the Rust compiler was able to be more precise? Because all of these issues are from forced type equivalences, where the Rust compiler forces two different types of variables to be the same. So if we do a more precise analysis, perhaps these pointers may affect fewer other pointers. So instead of looking at unsafety directly, we're going to use the proxy metric of assuming one of these pointers was unsafe, how many other pointers would it affect? And we have 4 different levels of precision. We have the original one, which is like the Rust system. And then we add in field sensitivity. Then we add in directionality and context sensitivity. So we can find that field sensitivity is somewhat useful here. It decreases it slightly, so it's not worse than nothing. However, the first major difference comes with the introduction of directionality, which I'll talk more about in a bit. And then after that, depending on how we structure this, context sensitivity is either a small boost or a very large boost to the limitation of the contamination spread. And the difference here is, well, if we split up our pointers based on which function, where the call site is of a function, then are we able to make some of them safe? Well, in that case, it decreases by 50 times. If we are required to make all of them, then it's 2 times. This P3, our directionality, is where the most significant drop is. So on this slide, you can see our 3 largest benchmarks. Going from P2 to P3, which is adding the directionality, increases the percentage of pointers that don't have a very large relative effect from less than a quarter to about 90% or more. Okay, so now I'm going to talk about directionality. So we can't make the Rust compiler add in this precision to the Rust compiler, first of all, because it would be a ton of work, and second of all, because it would really increase compile time, and Rust already kind of has an issue with that, and we don't want to add on to it. However, we can take our code and modify it so that the compiler is able to read it as directional automatically. And these changes that we're adding are going to add in real safety. So this isn't fake safety, but the real kind. And just to give an example of this, if we have 3 pointers, our x, y, and z pointers, and we originally set z to y and then z to x, and one of them has to be unsafe, so let's say that our x has to be unsafe, then as a result, because z comes from x, then z also has to be unsafe. And then because the types of y and z have to be the same, then that forces y also to be a raw pointer. It can't be a reference here. So this is one example of this massive spread of unsafety. However, we can add in these blocking points. So we can add in that z is y as a pointer. And this allows y to still stay as a reference. The compiler can notice that, okay, y and z don't have to have the same type. So y can be a reference while leaving x and z, which have to be raw pointers. So this actually has a good result. So originally, with our pseudo-safety, only 12% of the pointers were made safe. But when we add in these casts, and if we do something with boxes, then we're able to increase the number of pointers made safe from 12% to 24%. And some of the programs don't have a major improvement. And these are ones that use function pointers, which we found very difficult to use with global pointers at the very beginning. And some of this is just inherent to the project of translating C into safe Rust. Like the structure of C code may be something that relies on programmer knowledge about the structure of the pointers. And so we can't get rid of it entirely. So as a result, the key points that we have is, one, we can use pseudo-safety if we want to isolate the effect of one particular thing. In this case, we wanted to isolate the effect of lifetimes. And so we use pseudo-safety to set aside all the other concerns. Second, we found that the primary challenge in translating C into safe Rust, in turning these raw pointers into references, is aliasing. And finally, we found that the Rust compiler, if we can add in this precision, then this can have beneficial effects for the ability to make pointers safe. So next steps, we might do stuff to mimic context sensitivity. We can't do this completely, otherwise the program explodes in size. We might add in stuff with structs to mimic the field sensitivity. And then we also might want to tackle these things that we set aside with pseudo-safety. So tackling how might we model pointer arithmetic, for example, or these globals or unions or so on. And if we can have a program analysis that says, okay, these pointers are the core pointers that need to be fixed, that these need to be made safe, and then as a result, a large chunk of your program is going to be able to be made safe as a result. And I also want to shout out, there was a paper citing us which uses Laertes as a baseline and does their own analysis, specifically focusing on the lifetimes and ownership, and they have some custom things, so you can check that out. It's called Crown. So thank you. Any questions?
Thank you for your talk. So as a client of a translation tool from C or unsafe Rust to safe Rust, I would be very interested in getting a readable idiomatic code. So the findings that you have presented, can you kind of comment how they impact the quality and the readability of the code that tools like Laertes can produce?
Okay, so unfortunately, the transpiler for C to Rust, it results, including with our additional going from unsafe to safe, the readability is not very good. So this is one of our possible directions for making the code better in the future.
And what are the main issues, like in producing idiomatic code?
Well, it's effectively a kind of synthesis, which is a difficult thing to do.
Thank you.
Hey, thanks a lot for your work. I think these are sort of early findings on how difficult this translation is going to be, so excellent work. My question is, you see, the difference between, let's say, C and Rust is not just one of a bunch of rules, right? I think you're lifting abstractions here in terms of these ownership types and borrow checking and so on. So I'm wondering if you went around and said, because the original C code is written with none of these disciplines, right? Did you think about refactoring that code to say that if I were willing to rewrite parts of C, then maybe this analysis would work out to be much, much more effective? So have you tried that?
This is something we've thought about. It isn't something we've done yet. So it seems like we can target specific patterns in C code to notice, okay, we can turn this, we can refactor this into a particular Rust program pattern.
Awesome, thanks.
Thanks for the talk. Do you see any performance penalty here when you're translating C to Rust?
So it's the performance. I mean, it depends on the size of the benchmark that you're translating. Unfortunately, we don't have it at under like 5 seconds or so for the very large ones, but we did make some performance improvements over the original Laertes if you've used that at all. Basically, like the time that we need for a compilation is also like the larger the compilation time, the larger this transpilation time is also going to take. But we don't do the transpilation. We're using the existing C to Rust tool.
I think a follow-up question to that. So have you finished you were able to cast some of the points as some of the pointers as safe, right? The rest of them unsafe. So were you able to run the evaluation studies on the unsafe part? Like, how does it compare to the one, in terms of performance to the original C code, right? Like how does
you mean in the program after it's been converted?
Exactly.
There shouldn't be any change in how fast the program runs because it's doing the same thing.
With respect to the original program and the final one?
Yes.
In C and Rust?
The dynamic semantics is the same.
Okay.
In fact, actually, I can say that one of the, if I go back to this here, the difference here between the 24% and the 21% is that with the 21%, we use something which has stronger guarantees of safety. With the 24%, there's a possibility of undefined behavior. And with the 21%, we use the box structure. And the reason why it goes down to 21% is that there are some cases where we can't actually insert boxes. Otherwise, the performance would have a negative effect on the performance.
Okay, thank you. Let's thank the speaker again. Our next speaker is Sivan Thai, and he's going to speak about adventure of a lifetime, extract method refactoring for Rust.
So, hi everyone. Can you hear me? So today I'm going to talk about extract method refactoring for Rust. My name is Sivan, and this is joint work with these lovely people. To get started, let's extract a method in Python. So here we have a program which manipulates two lists with some aliasing and then print the value of z here afterwards. We want to extract this conditional branch, which will assign the value of z a local variable y in one branch and a global one in the other. So let's extract it, produce something, let's run it, and it works. Now, let's try a similar program in Rust. This is just where we made all the references more explicit. So let's try it. It produces something down here. Let's run. And oh no, it didn't work. The compiler is complaining. So extracting a function in Rust is actually non-trivial. Why is that? What are the challenges of extracting a function in Rust? So in Rust type system, every value has an owner. And there is a set of rules to allow other entities like a function to use the value by borrowing or taking ownership of it. And in extracting a function, we need to take those rules into account and make the borrows explicit. So the extracted function has the necessary permission to complete operations like mutating a string. And those borrows have lifetime, which we've heard something about in the previous talk. This is how Rust type system calculates something similar to a scope. This is done using what is called the borrow checker, and it allows Rust to safely manage memory at compile time. This avoids things like dangling pointers by making sure that the pointer references a value with the same lifetime. Another challenge that we faced, but I won't go into detail, is we had to propagate the non-local control flow, and it wasn't done well in IntelliJ, which we built on top of. So one important observation is that the extracted function just now is actually almost correct. If you give this to a Rust developer, they would simply correct the level of borrows and ownership, and then add some lifetime annotation, and then we'd have a extracted code that is acceptable by the compiler. So our main point is actually Rust extract method refactoring is a repair problem. We just need to apply the patches in the correct order. So we have implemented our solution REM to do specifically that. So we start with the normal IDE extraction, where a developer would use the UI and then get a hoisted function with a call site where the function body was. And then this is where, in cases like Python, the extraction is successful and we can stop. But for us, this is not enough. The hoisted function is still broken. So now we start our refactoring as a repair pipeline, where we first fix any non-local control flow. We then do a static analysis to determine the level of ownership and borrow that the extracted function needs. And finally, we set up the initial lifetime annotation in the extracted function and use an oracle to determine the fixes to those annotations. So let's go back to our example in the beginning and go through the pipeline step by step. So first, we hoisted the function, and we see that it doesn't work yet. We're here now. Skipping the non-local control flow fix, we now have to do some static analysis on the caller and the extracted function. We collect constraints about usages, aliases, mutability, and definitions, and then we use Prolog to solve those constraints, determining whether the extracted function needs to borrow the value or it needs to own it. Briefly, we see here that y is aliased by z, and since we use z, we need to also be using y, and therefore the function needs to borrow y and not take ownership of it. We patch the call site to borrow y, and then we patch the signature as well as the extracted function body to treat y as a borrow. So after we patch the necessary borrows, we need to give those borrows lifetime annotation. We start by annotating all the borrows with unique lifetime, meaning that we initially expect all of them to have different scopes. We start with LT0 for the first input reference xref up until LT3 for the output lifetime. And now we need to ask an oracle. Here we're using cargo check to invoke the borrow checker to see if our annotations are actually correct. If cargo check fail, it'll give us a way to relate the lifetime together. That means for the function to be safe, the borrow checker needs the lifetime to be bounded together, i.e. like lifetime 1 needs to live at least as long as lifetime 2. In this case, since in one branch we return y as a borrow, we need to make sure that the input lifetime for y, which is LT2, is related to the output lifetime LT3, and the borrow checker tells us exactly that. So we add this bound, and now we have an extracted method in Rust. Let's do a demo of that. Which is using our own solution. Yeah. Okay. That is weird. There we go. And we have this extraction, which is apparently not working. Sorry, give me a second. Oh, there we go. It was just happening on my screen and not on the shared screen, sorry. So let's run it. And voila, we have our extraction. Yeah, sorry, there was a bunch of prompt that was happening on my screen and not the actual slides. So here, we have the demo. So now let's see how REM did. We evaluate REM using 3 research questions. So is it practical? That is, can it produce good extraction most of the time? And will the code that it produced be similar to that of a Rust developer? And is it efficient? How long do we wait on average for an extraction? And 3, we compare it to existing implementations, which are the IntelliJ Vanilla plugin that we built on top of, and also the Rust Analyzer plugin for VS Code. We run 40 extraction on 5 real-world projects that are quite popular. And we covered a variety of code features in the extraction, such as extracting breaks and continue from loops and extracting returns. We also extracted function that requires mutable and immutable borrows. We extracted function that needs to have its lifetime annotated. And we also extracted function that uses structs that have lifetime slots in them. We do 3 types of extraction. We inline existing function, and then we re-extract it using REM. We also do random extraction, and then we try to go through version control to find where developers have actually done extractions and try to redo that with REM. There are 3 outcomes. Good extraction produce compilable code. Bad extraction produce non-compilable code. And no extraction means that the tool recognizes it cannot extract and then informs the user. So this is our result. Let's dive a bit deeper. So is it practical? REM produced good extraction in 37 out of the 40 cases that we had. And in the 3 cases where we couldn't, we informed the user. And the extracted code is similar to the developer version with some minor caveats. So let's look closer at experiment 19, where we inline the decode function and then re-extract it. There's only 1 lifetime specified in the developer version, so the borrow checker expects everything to have the same scope. In REM's version, the lifetime is bounded a bit looser. It is more permissive because our repair process actually only bounds the necessary lifetime together enough so that the function is safe. And here we can technically have the borrow I with lifetime LT0 being dropped before the borrows in T1 and T2 with lifetime LT1. But in the developer version, I must live as long as T1 and T2. So in this case, I think REM is practical. And on average, REM takes about 1 second to produce extractions. We found that using cargo check is actually not the end of the world. Once the project is compiled once, the check is only done on the modified file. And while IntelliJ and VS Code produce extraction instantaneously, I think this is still a good enough efficiency for us to use during development. And even in our worst case, where we needed 3 Oracle invocations, we only took around 2 seconds. And our implementation efficiency actually varies more with cargo check cycle than it does with the project or file size. So yes, REM is also efficient enough. And while we successfully refactor most of our cases, IntelliJ and VS Code completed about 50% of them. with notably IntelliJ and VS Code failing on lifetime-related refactorings, and IntelliJ also sometimes fails on the borrows as well. So it is more effective in that sense. And there are some limitations of REM. So first, we don't support generic trait bounding. We can probably apply the same repair that we use for lifetime, but it needs to be reasoned about more. And we also currently rely on IntelliJ for type inference that we use for our borrow analysis. And IntelliJ like to re-implement what the compiler does and be just on its own, standalone. So if anything were to be discrepancy between them, we also have that. And for further work, since our pipeline is mostly in Rust, we can basically have a front end for VS Code for Rust Analyzer to use. And we can also need support extracting trait bounds and other features. So to conclude, we found that extracting a function in Rust is non-trivial. But refactoring in such a complex file system can be decomposed into a series of modular repair problems which are easier to solve. And we implemented this idea as a robust and efficient plugin. Thank you.
Hi, thanks for the talk. So suppose you've got a novice Rust programmer, and they're doing some Rust programming, and they've got some errors that they're not sure how to resolve. Could they take your modular repair mechanism and apply it to their code and hope that it might help them with their misunderstanding of Rust situation?
That's a good question. One of our limitations as well is that we require the project to be in a compilable state, but there is something that we can do to remediate that. We need to basically kind of mock the environment so that it is somewhat compilable. But in that sense, I don't think it would actually provide the feedback that the Rust developer need to fix their problem. It would just help with the extraction.
It would just help, say again?
It would just help with the extraction process, yeah.
But it seems like you first extract and then you do a bunch of fixes.
Yeah.
So could you take those fixes and apply to something that didn't result from an extraction?
Yeah, I see what you mean. Yes, because our pipeline is actually decoupled. We have actually 3 different binaries in Rust for that, and you can technically apply those into the program, and then it would result in some fixes. It may not be, because we apply them in the context of the refactoring, and we kind of know what is expected before and after.
Sure.
So I'm not sure how it would play out in a random piece. Good.
This is very cool, but it's also quite complicated. Do you have any thoughts on choices the Rust language designers might have made to make this kind of refactoring simpler? How could language design have been changed to make this a little less painful?
That's a very interesting question. I'm not sure, because this was mainly a feature for safety, for memory safety, which, as we learned from the previous presentation, is complex because otherwise it would cause a lot of problem like in C. I'm not entirely sure if there's a better solution to do this that would make it less painful, but yeah, I don't see it as avoidable.
Thanks for a cool talk. How feasible do you think it would be to avoid all these many different lifetimes on the extracted method and collapse some of them in a way that the programmer seems to have done?
So sorry, could you repeat that?
Yeah, sure. How feasible do you think it is to sort of avoid having all these extra lifetimes and extra bounds and collapse some of them, even though it makes it a bit less general?
So this is already collapsed, and we can kind of collapse it further and constrain it further. But we were trying to constrain the amount of time we try to invoke the oracle, because the more constrained that we are, we actually might need to loosen it back so that it compiles. So yes, it is possible. It just probably will require a few more invocations.
Thanks.
Hi. So is there any completeness argument on refactorings, like in terms of lifetime inference? Is there any completeness argument with respect to refactoring?
I'm not entirely sure.
Okay.
In terms of like...
So lifetime inference is something which is also done in, for instance, region-based memory management, right? So you could have principal typing, which means that there is a principal lifetime allocation for variables. So in that sense, is there like a principal, like do you know when you have converged, for instance?
We tried that approach, but the problem is that actually the current Rust type system is not fully formalized yet. We have Polonius, but it's not completed. Okay. So it's hard to actually have a principled approach to fix the lifetime. That's why we kind of decoupled it so that we have principled approach to fix the local control flow, the ownership, but we couldn't really do it for the lifetime. So that's why we used the repairs instead.
Okay.
Thank you.
Okay, let's thank the speaker again. Our next speaker is Jack Fesser. He's going to talk about inductive program synthesis guided by observational program similarity.
Great, thanks. So this is joint work with my old advisor, Armando Solalazama, and Ishil Dillig. Before I start telling you about the things that are new, I want to do a brief recap of synthesis with bottom-up search. So here we have a little arithmetic DSL specified by a grammar E, and we'd like to find a function f that satisfies some input-output examples. The simplest thing we can do is to just start enumerating programs, starting from small programs, and building larger and larger programs by composing the programs that we've already found together using the operators in our DSL. This works just fine. The downside is, of course, that the space grows very quickly. And so in practice, we often want to apply some kind of optimization to this kind of synthesis. In particular, it's very common to use an optimization called observational equivalence reduction. And observational equivalence reduction takes advantage of the observation that if we have programs P and P prime, and they do the same thing on some vector of inputs I, then it's always safe to treat P and P prime as if they were equivalent during synthesis, even though in practice they are probably not actually truly equivalent. So the way this works, it is a slight modification of our previous approach. We build our programs from the bottom up in the same way, but in addition, we keep track of the behavior of those programs on our inputs I. So we form a characterization vector, and we use those vectors to cluster programs together into equivalence classes. And we only retain one program per equivalence class. So when we go back to our example, and we run this, what we see is a very nice reduction in the size of our search space. We find our answers more quickly. Everyone is happy. The downside is that this doesn't work in every domain, and we ran into a couple of domains where this really very much doesn't work. So to give you an example, consider the inverse constructive solid geometry domain, or inverse CSG. So the goal here is to start with a picture like we have on the left, and to write a program that generates that picture by composing primitive shapes like circles or rectangles, using Boolean operations like plus and minus, and other operators, like in our DSL, we have a kind of repetition construct. So if we think about this DSL, we immediately run into a fairly difficult problem when it comes to the use of observational equivalence. And that problem is that this DSL produces an enormous number of very, very similar, but not exactly equivalent programs. So here we have all the different ways that you can take the center out of a circle. And if we just shift or scale or move that center slightly, we get a program that is distinct from the perspective of observational equivalence, but that is very much not equivalent to the program, to the other programs in this set. So small program changes result in small behavior changes, but those behavior changes mean that these programs are not equivalent. So observational equivalence really falls down in this domain. But as a human, our insight is really that any one of these programs should be fine. We could replace one with another, and we would end up with a small perturbation in our output, but we could probably repair that perturbation after the fact. So we extend this insight. We basically take this insight and we say, okay, well, what if we used similarity as a kind of replacement for equivalence? We say that programs P and P prime are observationally similar if the distance between their behavior on some inputs is less than some epsilon. So here, this distance d, this is going to be specific to the domain that we're working in. So what happens if we do this? What happens if we replace equivalence with similarity? We define similarity classes that are analogous to equivalence classes, and we keep a single representative for each class. We, of course, get a reduction in the size of the search space. We are clustering programs together. But we also get error. Essentially, what we've done is we've said, well, our representative program is going to be the circle with a square taken out, and it's similar to everything in its class, but it's not the same as the circle with the circle taken out, so we can only generate this close but incorrect program. So if this is going to be useful, we have to come up with some way to mitigate this error. And what we have found is that in practice, this error is actually very mitigatable. And what we can do is we can take a program that is close but wrong, and we can attempt to repair it. And in our work, we use a rewrite system. Essentially, we apply rewrite rules. We guide the application of those rewrite rules using our distance function. So we perform a kind of hill climbing search, applying the rule that moves our erroneous program closest to the goal program. And we repeat this until we find a correct program or we fail. So at this point, we essentially have a synthesis algorithm. We perform a bottom-up search, very analogous to the kind of bottom-up search that we would perform with classic equivalence reduction. And then when we have finished building our search space, this is, if you're familiar with FTA-based synthesis, this is a very similar data structure, but instead of representing the programs that satisfy some examples, we represent a space of programs that almost satisfy those examples. We then extract programs from that search space, and we apply rewrite rules to attempt to repair them. And we repeat this process until we solve our problem. So the bottom-up search looks almost exactly the same as it does for standard synthesis with equivalence reduction. We repeat an expansion step where we generate new programs by composing programs we have found. And then we perform a clustering step. This is analogous to equivalence reduction, but in our case, we're doing clustering. We're building clusters of bounded radius using our distance functions. We then perform a ranking step to attempt to select the clusters that we believe will be most useful in solving the overall problem. We retain those top K clusters, and we continue building our space. In our implementation, we build this space up to a bound, and then we begin extracting programs from that space, picking programs that are accepted by states in our finite tree automaton that are closest to our goal. We extract programs, and we incrementally repair those programs by applying rewrite rules guided by our distance function and the goal behavior. So in practice, this algorithm is pleasantly general. We can parameterize it over our domain-specific language, which we give by a grammar G and an evaluation function E. We also have to provide a distance function delta that tells us something about the similarities between program behaviors. And we have to provide rewriting rules R that we use for repair. We chose to use rewrite rules because they're a little bit more flexible than something like gradient descent, although gradient descent, I think, would likely work here. But rewrite rules allow us to do both continuous changes, like scaling or moving or resizing, and also non-continuous changes, like this translation from circles to squares, which turns out to be important for the CAD domain. OK, so we implemented this algorithm, and we parameterized it for 3 fairly diverse application domains. Inverse CSG, which we've talked about. We also looked at a tower building domain, which is a kind of AI task, where you're controlling a little robot arm that moves left and right across a playing field, and it drops blocks to build towers. And then finally, we looked at a regular expression building domain. So let's look at some results. So for inverse CSG, you might be able to tell, this is the domain that we designed the system around. So the performance is quite good. This was really our motivating domain. Here we look at 25 randomly generated benchmarks, 22 handwritten benchmarks, and we compare against 3 baselines. First, we compare against an instantiation of Sketch. This was used successfully for inverse CSG in prior work, but it's very brittle. So changing the DSL in any way causes that technique to collapse. And so when we looked at it, what we found is that it really was not able to perform very well because the DSL was modified in a way that caused the Sketch algorithm to really change its performance characteristics. We also looked at bottom-up enumeration, which is the blue line. And we looked at an instantiation of an abstraction-guided search. So we built an abstraction that we used for clustering in the abstraction-guided sense. In all of these cases, we found that the baselines were quite bad at inverse CSG, and this is part of the motivation for looking at this problem. Looking at the regular expression domain, we see that the baselines are quite a bit stronger, but we are still outperforming them. Here we look at the prior state-of-the-art. It's a tool called Regel. It's a top-down synthesizer, and it uses some very clever solver-based pruning techniques. We also looked at bottom-up enumeration and abstraction-guided search. And what we see here is that bottom-up enumeration, the blue line, FTA, is actually quite strong. But where it starts to fail is where it starts to hit its memory limit. So what we see is that our algorithm is equivalent in performance to bottom-up search in this domain, but it's less memory hungry. It needs less space to represent its programs. So it's a little bit better suited for maybe more memory constrained domains. And so that's where we see that performance improvement. And then finally, we looked at a tower building domain. This was drawn from some work in the more AI side. It came from the Dreamcoder paper. And here we compare against a neural method from Naya et al. We also compare against bottom-up enumeration. We actually don't compare against abstraction-guided synthesis here, and there's details in the paper. This actually turns out to be a fairly difficult domain to instantiate that technique in. And we think that this maybe indicates that it's a little bit easier to instantiate this similarity-guided stuff in some domains that are harder for techniques like abstractions. Here we don't see the performance achieving what we can do with a neural method, but I think we're fairly competitive, and we have the pleasant benefit of not requiring a training step. Okay, so the last result I'd like to share with you is a little ablation study that gives you a sense about what parts of the algorithm are most important. So here we looked at our algorithm, the full thing, it's on the top, and then removing various pieces. So this is for the inverse CSG domain. And what we can see is that if you basically make the repair step random, if you randomly explore repairs, the whole thing collapses. The repair step is very, very important. If you turn off ranking, again, the whole thing collapses. So picking clusters that are close to the goal program is also very important. Clustering and the technique that we use to extract programs from the search space are both important, but they are less important than ranking and repair. And that this distance function that we choose, we used a custom distance function for this domain. It's a small variation on the Jacquard distance. It's explained in detail in the paper. We wondered how much that domain insight mattered. And so we turned that off, and we found that it does matter, but pleasantly, it doesn't matter as much as the other parts of the algorithm. So you can get away with relatively simple distance functions. They don't have to be tweaked perfectly for the domain, but tweaking them more does improve performance. Okay. So to conclude, we've presented an algorithm that uses the similarity between programs to cluster them as we search. And we've shown that this can actually significantly improve performance on some of these interesting sort of continuous-like domains, like inverse CSG, and that we can recover from the error that we introduce with that clustering by doing a kind of hill-climbing search. We think that this algorithm could be applied in a number of other domains, and I'd be very interested to see people use it in other places. I'd also love to see, there's a lot of interesting future work here, and one thing I'm interested in looking at is trying to take some of the expert knowledge out by replacing the distance functions with some kind of learned distance. The challenge here is that these distance functions are extremely performance sensitive, so any kind of learning would have to be quite performant. But that would be interesting to see in the future. All right, so thanks so much for your attention. I'd be more than happy to take questions.
Thank you very much for the very interesting talk. So I think your approach depends on the property of the domain, that the similarity between the output of the program indicate the similarity of the program themselves. Otherwise, you cannot repair them. So yes. I'm wondering to what extent this property holds. You have already shown, at least in 3 domains, the property hold. I'm wondering if there's a general characterization to what extent it holds.
I think characterizing this kind of property in general would be very interesting, but I think any sort of characterization that's sort of parameterized over the space of domains is, you're asking a really wicked question here. We talk about this in the paper, so we give some formal requirements to get completeness. One thing I didn't say is that this algorithm is not complete unless you satisfy our requirements, and our requirements are very strong. So we have some sense of what you need to do to make this complete. Most domains I don't think satisfy it. I think the takeaway for me here is that you can get much better performance than some of these complete techniques. So if you want an answer, try this, but it may not give you as many guarantees as you would like. Does that address your question?
Yeah, I think so.
Okay, thanks.
Thank you.
Oh, hi, I'm Joseph from University of Edinburgh. You mentioned that to build, let's say, the initial space, you still use like enumerative search to build like the initial space and then the clustering thing.
So the clustering is interleaved. Basically, if you know how a bottom-up search works, you're expanding and then collapsing into equivalence classes. Replace that collapsing step with a clustering algorithm. We use something custom because we want clusters of bounded radius. So like k-means doesn't work.
Yep.
Sorry, I kind of cut you off.
So yeah. So my question is, when you just pick up like one representative program per cluster, so you make sure that you don't waste a lot of time exploring programs that are similar itself. My question is exactly when do you like decide given you're in a cluster and you did not find your answer with your repairs, how do you decide which cluster you will go next? Like, is it also based on the distance function?
We look at the clusters in order of their distance to the goal, and we spend a fixed, basically it's a hyperparameter that tells us how much time to spend on each cluster.
Oh, okay.
Yeah.
All right. Thank you.
Yeah.
For distance function, what is the distance function for the other two domains that we have in the benchmark? So for X and
so for regex here was it's example driven. So we're looking at the actually the match sets, so the places in the output string that match, and we're looking for how many examples we get, and for the examples that we don't get, whether or not we even match the part that we're supposed to match, even if we match other places. I would have to check the paper for the exact details on that one. On the tower building domain, we take advantage of the insight that in this domain, it's actually quite easy to translate the towers left and right. That requires a very small program change. So basically, it depends on where the arm starts. So the distance function is sort of translation invariant, but it pays much more attention to the shape of the tower. So it normalizes and then does a distance comparison. So the distance function is really encoding quite a bit of domain knowledge here.
Okay.
Does that help?
Yeah, that helps.
Okay.
Hey, okay. So the question I have is, when you want to learn a function f, typically you think about how many examples I have to show the system so that it can learn f, right? So did you also notice that as you go on showing more and more examples, even without the repair process, you're converging to the right answer? Did you observe this phenomenon in your experiments?
We didn't try giving it more examples in kind of an incremental way.
Okay.
For CAD, the examples are not independent, so you really have to give them all. For regex, you could give the examples independently, and for towers, the example, there's only one example, it's the single tower. So there's not really an incremental process here.
Okay, got it, thanks.
Yes.
can you get the feet? Great. So our next talk is from Jocelyn. She's going to talk about automated translation of functional big data queries to SQL.
Thanks for the introduction. So I'm Jocelyn. I'm going to present this paper for my colleagues on automated translation of functional big data query to SQL. So the joint work with Guangcheng Zhang, Ben Mariano, Xipeng Shen, and Ishil Dilek. I'm not on the paper, by the way, so. So first of all, let's start with what is functional big data query. So functional big data query, let's look in the context of example, is a program that looks sort of like this. A functional query is composed of invocation to second-order APIs, such as flat map, map, and reduce by key. These APIs usually take first-order UDFs as argument. The UDF are written in general programming languages, such as Scala and Python. The good thing about functional big data query like this is that they're very expressive. You can see, like, for example, the UDF can, basically you can use whatever programming language you like. However, it's very less performant than SQL. So to get why this is the case, let's look into a context of example. So here, we want to have the input table have 2 columns, last name and the first name. I would like to write a query that generates an output table where the first column indicates distinct last name in lowercase. The second shows how many people have the same last name. And lastly, what is the length of the longest full name for each of the distinct last name. Here, I show you the program that will write in order to take this input table to this output table in both Apache Spark program and also SQL query. So as you can see that, the first thing I would like to highlight actually is that SQL query here is 11 times faster. So furthermore, the 2 programs actually compute in the output in a very different way. Consider the diagram in the bottom of the screen, which shows the execution of the 2 programs on a particular input. The top part here over here shows the execution of the Spark program, and the flow down here shows the execution of the SQL query. So for the Spark program, it first converts the last name to their lowercase, and then group all the users by the last name. By the last name, it then maps those users to the last 2 columns by getting the size and max length. On the other hand, the SQL program works very differently. It first casts each last name to lowercase and compute its length of the username by summing the first and last name. And then it groups the user by last name and takes the maximum of the full length. So you can see that not only these 2 programs look very, very differently, but they're also very different in semantics. So this imposes a huge challenge in terms of when we want, given a Spark program, how do we convert into a SQL query that hopefully to be much more performant? So our solution is to rely on a concept that we call column-wise decomposition. The goal for this example is to design a program that can produce the table on the bottom given the input table on the top. Our central idea is to synthesize 3 different programs, 1 for each single column, and then merge them together to retrieve the final program. Here, as you can see there, on the left, we synthesize 3 different separate SQL queries for each of the columns, and finally merge them back together to get the full program. In order for this approach to make sense, there's a key thing that we need to verify to be true. First, synthesizing each single column queries should be much more efficient than synthesizing the full program query. And second, merging them must be really efficient. So are these things true? So in order to, well, of course, these are true, but these are true based on 2 key observations. Our solution relying on 2 observations, and first, queries for individual columns of the output often share very similar structure. And second, queries that share a similar structure can be easily merged. To give you an intuition for why this is the case, let's look at this example. On the right, I show you the full query we would like to synthesize. And on the left, I have pictured 3 column queries, which each produce 1 of the 3 expected column output. On the initial inspection, hopefully you can come to the conclusion that these column queries look somewhat very complicated. However, if we take a closer look, we realize that large part of the column query are actually shared. Only the portion I outline over here actually differ between various column queries. This is the heart of our first observation, that much of these column queries are actually the same. Additionally, we notice that we can actually construct a full design query by keeping the shared portion of the column query and then concatenate them together, the remaining portions, which is And this corresponds to our second observation that the column query with this structure can be easily and efficiently merged. We operationalize these observations in an algorithm that takes advantage of what we call a dependency-free query sketch, or DFQS for short. A DFQS is a partial SQL query which takes two key properties. One we call a syntactic property, and one we call a semantic property. The syntactic property restricts where hosts can appear in the program to only projection and aggregation operations. The semantic property ensures that complete sub-extraction of DFQS must evaluate to the same value on any completion of DFQS. While this definition might seem a little bit complicated, each part of the definition serves a key role for our algorithm. The syntactic property ensures that column queries can be efficiently merged into a complete query. Meanwhile, the semantic property is the key to ensure that our efficient merging procedure will always produce the correct complete query. Here you can see a DFQS that is used for our running example. This query has both of properties listed above. Okay, so now we understand the general idea of DFQS. How do we put it into a synthesis algorithm? Our algorithm starts by splitting the functional query into one functional query for each of the columns. These programs can be trivially obtained using the map operator of most functional query language to retrieve the ith column. So suppose in this case I have a table with n column, we have 1 to n columns separately. Then each column function query is passed to a counterexample guided inductive solver along with the DFQS produced by the DFQS generator. Anytime that any column query, since this problem fails, the DFQS generator is queried again for the next DFQS, which is then sent to the CGIS solver of the new column queries. Eventually, when DFQS is found such that all column queries can be successfully synthesized, those queries are merged together to produce the final desired query. Because we have limited the query to be instantiations of DFQS, we can efficiently syntactically merge these queries. We now know how we can operationalize the DFQS in an algorithm, but it leaves the last important question to answer. How can we efficiently enumerate DFQS so that this approach is actually efficient? Well, the way we do that is we adjust the algorithm that we showed previously. And in this new algorithm, we first synthesize one of the column queries at random. You can be any columns, with no DFQS. Then we pass this generated column query to a DFQS extraction algorithm that extracts DFQS from a column query. Intuitively, this procedure keeps a concrete sub-expression of the query that are necessary to maintain the desired properties of DFQS and replace all the other hosts with hosts. Once the query sketch is generated, it is used as a DFQS for all the other synthesis problems for the rest of the column. If any of the column synthesis problem fails, the synthesis procedure for the base column, the one we start with, is invoked again and to produce a new column query and a new DFQS. This process continues until a correct column query is discovered for all the columns, at which point the results are merged and the final query returned. To assess how good our approach is, we built a tool called RDD2SQL and evaluate on a benchmark set we collected. To collect the benchmark, we download all GitHub repos with at least one start and one call to the Spark RDD API. We then extracted all non-trivial programs from the set and randomly sample 100 programs. So here we show some statistics of the gathered program shown on the bottom of the slides. And as you can see, it's fairly complex in terms of line of code and AST size. The first question we want to answer is how well our proposed synthesis or transpilation algorithm works. So this graph, we run all the benchmark within a 1-hour limit. The graph shows the percentage of benchmarks solved on the y-axis and the time it took to solve on the x-axis. As we can see, RDD2SQL can solve 98% of the benchmark within the time limit and actually solve most of the benchmark within the first 7 minutes. We also compare RDE to SQL to two different extensions of CLIS, an existing synthesis tool for query optimization. The graph here shows the number of benchmarks solved on the x-axis with the cumulative synthesis time in seconds on the y-axis. As we can see from the graph, neither of the extensions of CLIS can solve nearly as many benchmarks as RDE to SQL. Lastly, remember that the motivation of doing this whole translation from RDE to SQL is that we want to get more performant query. So how performant is actually the query that was synthesized? So we evaluate how big a performance gain we can achieve using the synthesized query as opposed to original ones. The average speedup of the synthesized query was 2 times with the maximum speedup of 7 times across a variety of cluster size and randomly sampled inputs. So in this talk, I discuss our algorithm for automatically synthesize SQL queries from functional big data queries. I first explain the problem and motivate why this is challenging. Then I also explain the key idea before our algorithm, column-wise decomposition. Then I explain our synthesis algorithm, which solved the problem by decomposing it into individual translation problems for each of the column. Finally, I show the result of our prototype implementation called RDE to SQL, which indicate our algorithm can successfully transpile a variety of queries, and our algorithm is able to transpile many more queries than other related work in the literature. Thank you so much, and happy to take some questions if I can answer them.
Go ahead.
Hi, thanks for the talk. I was just wondering, so your input is kind of arbitrary functional programs.
Yes.
So do you have any kind of statement about the completeness of your technique? Under what conditions can you actually generate SQL? Is there some sort of restricted subset for which that's practical? Have you thought about that? Thank you.
Okay, so I think that's a good question. And in terms of completeness, I'm actually not sure for arbitrary function query, you can actually do that. But I think I asked the author for that, so I give you the answer I get a while ago. And it seems like they collect a couple very commonly used from GitHub, and it seems they're able to synthesize from a SQL from those queries, and they are correct. So in that sense, it should be probably there's no completeness guarantee for any functional queries, but for common one, it should be sufficient.
Okay. So are there any queries that sort of compile to joins in SQL?
Sorry?
Are there any functional queries that compile to joins? Like joins?
I think so, yeah.
Okay. Could you give me a statistic on what proportion of these are join queries?
Oh, that's a great question, and I have to refer you to the paper.
Okay. Fair enough. And one more question. So with respect to speedups, so what are the speedups in relation to? Like there are 8 machine ones, 16 and 24.
Yes.
So these are speedups of the compile SQL with respect to the original.
Yes. Yes,
okay.
Exactly.
And how was the SQL executed across? Like, what was the runtime for SQL to execute across 24 machines or so?
You mean how long the SQL execution time is?
No, I mean in general, the SQL runtime is single database or single thing, right? So how was it distributed across 7 or 24 machines?
I actually don't know, and you probably have to ask the author again.
Thank you.
Yeah.
More questions? Okay, let's thank the author. Our next speaker is Bo Wang. He's going to talk about user customizable transpilation of scripting languages.
Oh, okay. So, welcome to the last talk of the day. I'm Bo Wang, a PhD student from National University of Singapore, and this talk is about automated code translation for dynamic typed scripting languages. And this is a joint work with my colleagues. So first, why do we need code translation or code migration? So one reason is that programming languages are evolving over time, and some languages that are popular 10 years ago are being replaced by newer languages, and people want to move to languages with better features and supporting ecosystems. Another reason is that people want to share the code with developers in other application domains. So this is similar to natural language that we might want to translate a book from one language to another to share the knowledge with more people. In code translation, where we have some libraries in one language, we might also want to port it to another. But one big difference compared to translating in natural language is that, unlike books, that the code repositories can frequently bump into newer versions. So let us look at a motivating example. So here, Bob wants to develop an app for a serverless platform, and he has some code written in Python that he wants to reuse. But the serverless platform only supports JavaScript runtimes, and they require the developers to write applications in JavaScript. So Bob wants to translate his existing Python programs to JavaScript. The details of the code here is not important, but notice that the program 1 uses third-party APIs provided by a library called NumPy, and the second program uses only built-in APIs from the Python standard library. So Bob wants to find automatic code translators to help him instead of doing the translation manually. He found a popular Python to JavaScript code translator on GitHub, which claims to support Python 3.9 to JavaScript code conversion, and we call it Translator G for convenience. Bob first tried to use Translator G to translate program 1. However, the translation aborted with an error message. It failed to translate the third-party dependency library NumPy. But Bob is not interested in translating this third-party library. Since there are existing many libraries in JavaScript that provide similar APIs, he expects the translation to leverage the libraries native to JavaScript, such as TensorFlow.js or Math.js. So Bob then tried to translate the second program using Translator G. And this program doesn't use any third-party libraries, so the Translator G can successfully output a translation. But if we take a closer look, you can see that this translation actually imports hundreds of functions that mimic the Python standard library. So the translation seems to be like doing the emulation of the Python runtime in JavaScript rather than express the same program in JavaScript code using the native APIs. The translation is also verbose with nested loops and temporary variables. So what kind of translation that Bob is aiming for? For the first program, P1, if Bob could do it himself, he would be using some third-party libraries that provide similar functionalities to the NumPy library in Python. For the second program, P2, he would prefer a translation that use native JavaScript APIs while written in a newer language standard of JavaScript, such as ES7. From Bob's experience, we can find that the code migration problem involves many factors. So first is that users have their different preferences on the generated code. Second is that there are millions of third-party APIs available to a language. And third, popular languages are evolving at a fast pace. These factors give us two observations. First is that there are usually multiple ways to translate the same code. And second, it is difficult for a translator to generalize to every program. Thus, maybe a better solution to code migration is to find better ways to build specialized code translators. For example, instead of building one translator G trying to solve all the translation tasks, can we build specialized code translators with low cost that perform well on specific tasks? So here we have several research questions. First, how much human effort is needed? And second, can they perform better than general translators? And third, can they work for various styles of code? So in this paper, we are making the following contributions. First, we propose a user-guided and task-driven design for building task-specific code translators. And second, we implement a prototype named Doglot, a user-customizable translator for Python to JavaScript code conversion. And third, we compare the Doglot with existing translators on 3 benchmarks, and it can translate 10 to 20% more programs correctly with low human cost. So now let us look at the workflow of using the Doglot code translator. So given a rule set, Doglot will try to use these rules to come up with a candidate translation. The translation will be checked by a tester. If the translation passes test, the candidate translation is output as a translated program. Otherwise, the error message will be fed back to the do-glot translator. The translator might keep trying to find candidate translations, and when they fail to find a new one, the error information and the partial translation is provided to the user instead. The user looks at where the translation gets stuck and write code snippets that demonstrate the translation of that piece of code. The code snippets are then sent to the rule inference, which will synthesize a translation rule and then add that to the rule set. The loop on the left is a machine loop, which is a frequent case and is fully automatic. The loop on the right is a user loop, where the user intervenes only when the translation is stuck. The code translation process has two outputs. One is the translated program, and the other is a rule set that produces the translation. Notice that do-glot is different from traditional code translator in two aspects. So the first is that the translation rules are synthesized from user-provided code snippets. And the second is that the translation process is iterative and automatically leverages test feedback from unit tests. For Bob's scenario, for the first program, he needs a rule set that translating NumPy API calls to Mass.js API calls. And he can either create one himself using the code snippets or get it from other users with similar needs. With this rule set, he can automatically translate program 1 into a JavaScript version that uses Mass.js as a third-party library. Alternatively, if we want to use TensorFlow.js instead of Mass.js, he can choose another rule set to produce an alternative translation. For the second program, Bob can use a rule set that translates NumPy to JavaScript ES7, which is a relatively new language standard. With the rule set, do-glot can convert the program into idiomatic JavaScript code that use language features available in this version of JavaScript language. For example, we can see the use of const, map, exponentiation operator, arrow functions, etc. Now let's look into some technical details. So first question is that in the do-glot user loop, how do we create translation rules through user interaction? Here is a step-by-step example. So assuming that we want to use do-glot to translate this Python program, and the initial rule set is not comprehensive. So do-glot finds that there's a missing rule for the list comprehension on line 2 and asks the user to provide a translation rule. The user will provide 1 or 2 pairs of example code demonstrating the translation. Notice that different users may want to use different language constructs and APIs. The code snippet is then processed by a rule inference module in do-glot. The rule inference module will then infer a rule that can perform the translation demonstrated by the code snippets, and then the rule is added to the rule set. The rule inference works purely at the syntax level. First, the code snippets are parsed into fragments of ASC trees. And then it will try to extract common patterns from the 2 Python examples, and it will do the same for the JavaScript code snippets. The extracted pattern is a partial ASC tree with holes in it, and then it will perform an edit distance comparison, trying to match the holes between the source pattern and the target pattern. After that, the patterns will form a translation rule. And the Q here means that the partial ASC to be translated, and this rule will reduce the translation of the list comprehension into the translation of the expression, the loop item, and the iterable. Now, assuming that we have enough syntactic rules synthesized from user, the second problem is related to the machine loop of do-glot, which is how do we choose the correct compositions of those syntactic rules? So this is a problem because that for one piece of source code, many rules may apply. So not all rule compositions result in correct translations. So for example, in the first column, we can see that some translations performed by blindly applying syntactic rules that each of them seems to be correct can result in syntax errors. The second column shows that there are multiple ways to translate if x in y, depending on the runtime type of y. So here, which rule to apply depending on the semantics and context. But we do not want to burden the user to specify the applicable conditions of each translation rule, as that will be like writing the compiler. Thus, how do we figure out which rule to apply when there are ambiguities? The method we use is to leverage both grammar and unit test feedback. For example, first we test the translated code, and the tester produces an error message saying that there's an error on line 2. Then doglot will find out the rule application that produces line 2. It will retry that part with other rule combinations that are valid according to the grammar and also trying to fix the semantic error. And this process is done automatically. So here is a 5x slowdown of doglot machine loop, resolving ambiguities in rule composition and automatically fix all the translation errors. The translation is done when the translation passes all unit tests, and the user can hover on a piece of the translation to see the mapping to the source code and the rule applied. Notice that the translation process is fully explainable and controllable. This is also an advantage over code translation using language models. To summarize, doglot is a customizable code translator with the following design goals. So first, it is low-effort customization achieved through synthesis of rules using code snippets. And the second, it is automated rule composition that is guided by the grammar and the unit tests. We evaluate doglot on 3 sets of Python programs with unit tests as our benchmarks, and each set has programs with different sizes and styles. So gigs4gigs programs are mostly old-style Python 3 procedural code, and the LeetCode programs are a relatively new set of programs collected from GitHub for a programming contest platform, which is mostly written in modern-style Python 3.9. And CTCI programs are also old-style Python 3 programs, but using object-oriented style. So we compare doglot translator with existing compiler-based translators and a large language model. The most popular and well-developed compiler-based translator is Transcript, which is written in more than 30K lines of code and has around 3K of stars. This chart shows the number of programs that passes unit tests when using all these code translators. It turns out that the doglot performs better than other approaches when equipped with a rule set with 142 rules. So this chart shows the human effort and the number of successfully translated programs for the gigs4gigs benchmarks, which has 700 programs in total. As more and more rules are added, the number of programs that can successfully pass the unit test is increasing. It turns out that for this specific code translation task, the human effort to create up to 142 rules is 360 lines of code snippets in total. And notice that this amount of effort is far less than developing a general translator, and also the doglot surpasses the general translator when the number of rules reach 100. We then reuse those 142 rules for other benchmarks. So for example, we tested on the LeetCode. At the beginning, this set of rules cannot translate any programs, and because the LeetCode programs are mostly written in like a newer version of the Python language. But 2 of the 3 compiler-based translators have the same issue that they just cannot support the latest APIs and type hints in the newer Python language. But however, for doglot, this is not an issue like after adding 16 rules, it is able to translate more programs than all the other approaches. And as we keep adding more rules, the number of successfully translated programs keep growing. We also observe the similar for the CTCI benchmark. We can see that doglot can easily adapt to those different styles of code and the language versions. So in conclusion, we implemented a prototype translator named doglot, a user-customizable translator for Python to JavaScript code translation. We show that we can build task-specific code translators that perform well for the specific task with relatively low human cost. And the user-customizable translator can adapt to different styles of code. The future work includes designing more expressive rule language so that less rules are needed, and we can also consider synthesizing translation rules using language models. The rule composition can also be improved to leverage static and dynamic analysis to reduce the number of retries. And thank you so much. I'm happy to take questions.
What is, in your approach, that connected with Python and JavaScript? Like, if it's rule-based, if I wanted a translator from Python to Ruby, will I have to change any of your code, or I just need to write my own rules?
Oh, I see. Yeah. So there will be minimum change to the system because currently we have it is based on tree-sitter. So it has a pretty printer based on tree-sitter, and we currently implement that for Python and JavaScript. But with the pretty printer for the Ruby, we are able to basically translate between all these 3 languages.
So, thanks for the talk. I guess the question that probably a lot of people have is, I guess Python and JavaScript in this case have no types. So have you considered sort of extending how you might extend the technique to handle sort of type languages? And I guess also present to this particular session, earlier on we had a talk about translating C to Rust. So do you think that aspects of the borrow checker might complicate, or ways in which you might mitigate around that? Thank you.
Oh, yeah, thank you for the question. Yes, so for typed language that is, using a GC, that might be easy. So that's my opinion, but I haven't tried that. But for C to Rust, that is quite difficult because of the manual memory management issue. So I guess mostly you can get something maybe functionally correct, if possible, but it's very likely to have memory issues, I guess.
Thanks for the nice talk. Have you thought at all about allowing library authors to provide their own rules? I think it would be very interesting if you could ship a library update that then automatically upgrades all the user code.
Yes. Actually, we try to have something like this so that maybe, in the future we might have a library with similar to git ignore, but we have something like a translation config, so that once the source library is updated, you automatically have the translated libraries in other languages. This is something like we hope to achieve. Yeah.
Yeah, I think that would be very cool.
Yeah, thank you.
Hi, can you elaborate a bit more on how you use the error message to generate the rules?
The error message only shows that the error message basically report why the program translation is stuck. And then the user need to intervene and see where is the error, so that basically maybe it try to fix, for example, line 5. It constantly, it try many times, but it still cannot fix the error, so that the user will come and see what is happening on line 5 and provide a new translation rule for the statement or expression.
So you only look at which line is from and which variable is from, but nothing more specific than that from the error message?
Yeah, so we're assuming that most of the time the user basically look at the error position, the lines, and that should be enough, like the type and the variable names.
One additional question is what happens if user give you the wrong rules?
Yes. So if the user provide a large number of wrong rules, then the system will have very bad performance because the retry is very inefficient. But if the user just happen to provide one a mistake, right, and then later the system can find this rule is never successfully applied, then maybe the user can consider remove that. Yeah.
Okay. And one question about evaluation. So the thing is your evaluation on your tool is human guided. So when you compare against other tools, do you try to let the human intervene with their tool as well?
Sorry, I didn't.
So do you use human feedback when you compare against your baseline as well, or you just take it out of the box?
Yeah, that's the difference between the general compiler is that the general compiler you don't need. The developer of the compiler puts in effort, but when you use it, you just click the button, right? But for the customizable translator, you do need constant intervention.
Yeah, but I assume for stuff like codecs, you can provide feedback as well.
Yes, in codecs you can provide feedback, but you cannot really control it in a way that always control it in a way you want.
Yeah, that makes sense. Thanks.
Great work, Bo. So I'm wondering, since your approach is example guided as well, so is it prone to overfitting, to overfit to the data? And if so, what do you do to overcome that?
Yes. So we cannot prove that there's no overfitting in the translated code. So rules can overfit. For example, in the worst case, you write a rule that only works for positive numbers, and then in your test case, there only exist positive numbers and it's pass all the tests. But we think so. This can be partial. So first, we need better unit tests, I guess, to really capture the intended behavior of the program. And at the same time, it also depends on the rule language. So if it's more general, then it might be less overfitting. Yeah.
I just wanted to clarify one thing. So So do-glot requires a suite of unit tests. So if you're going from like one language to, like from Python to a later version of Python, you could just reuse the same suite of unit tests. But if you're going from like Python to JavaScript, does the user have to provide that suite of like unit tests themselves?
Oh, so here actually for all these benchmarks, we did some just basically string replacement to convert the unit tests. And because most of the time the unit tests are just a bunch of assert equals, and so we basically just doing string replacement is sufficient to convert the unit test, like also make sure it's correct. Because the translation of the unit test is usually much easier than converting the code.
Got it. Okay, thank you. Okay, last question. So there are features that are not common in both languages, right? For instance, it's possible to get dynamic scoping in Python. They could get right closures with dynamic scoping. What would you do in case if it's not, like, if there's no direct correspondence between one feature in this language to the corresponding feature in the language?
Yeah, I mean, so in the extreme case, we might consider Haskell and Python, right? Then maybe, because if there's too much difference between the two languages, then I don't think like this style of rule language will work. Yeah, maybe we need to find better rule inference languages or some other technique, or program synthesis, which will be more similar to synthesis, I guess.
Okay. Thank you very much. So that's the last talk of this session, and also last talk of the UPSLA. So thank you for coming.